This figure includes 4 photographs. The first is of an orange and black butterfly on a large leaf. The second shows a seam on a worn pair of blue jeans. The third image is of a red plastic drinking cup. The last image shows the blue flames of a lit burner on a gas stove. Figure 20. All organic compounds contain carbon and most are formed by living things, although they are also formed by geological and artificial processes. Credit left, modification of work by John Sullivan. Credit left middle. Modification of work by Deb Tremper. Credit right middle. Modification of work by Ansip/Wikimedia Commons. Credit right. Modification of work by George Shucklin. Chapter outline. 20. 1 hydrocarbons. 20. 2 alcohols and ethers. 20. 3 aldehydes, ketones, carboxylic acids, and esters. 20. 4 amines and amides. All living things on Earth are formed mostly of carbon compounds. The prevalence of carbon compounds in living things has led to the epithet carbon-based life. The truth is we know of no other kind of life. Early chemists regarded substances isolated from organisms, plants and animals, as a different type of matter that could not be synthesized artificially, and these substances were thus known as organic compounds. The widespread belief called vitalism held that organic compounds were formed by a vital force present only in living organisms. The German chemist Friedrich Wöhler was one of the early chemists to refute this aspect of vitalism, when, in 1828, he reported the synthesis of urea, a component of many body fluids, from non-living materials. Since then, it has been recognized that organic molecules obey the same natural laws as inorganic substances, and the category of organic compounds has evolved to include both natural and synthetic compounds that contain carbon. Some carbon-containing compounds are not classified as organic. For example, carbonates and cyanides and simple oxides, such as Co and Co2. Although a single, precise definition has yet to be identified by the chemistry community, most agree that a defining trait of organic molecules is the presence of carbon as the principal element, bonded to hydrogen and other carbon atoms. Today, organic compounds are key components of plastics, soaps, perfumes, sweeteners, fabrics, pharmaceuticals, and many other substances that we use every day. The value to us of organic compounds ensures that organic chemistry is an important discipline within the general field of chemistry. In this chapter, we discuss why the element carbon gives rise to a vast number and variety of compounds, how those compounds are classified, and the role of organic compounds in representative biological and industrial settings. Learning objectives. By the end of this section, you will be able to explain the importance of hydrocarbons and the reason for their diversity, name saturated and unsaturated hydrocarbons, and molecules derived from them, describe the reactions characteristic of saturated and unsaturated hydrocarbons, identify structural and geometric isomers of hydrocarbons. The largest database, one of organic compounds, lists about 10 million substances, which include compounds originating from living organisms and those synthesized by chemists. The number of potential organic compounds has been estimated to at 1060, an astronomically high number. The existence of so many organic molecules is a consequence of the ability of carbon atoms to form up to 4 strong bonds to other carbon atoms, resulting in chains and rings of many different sizes, shapes, and complexities. The simplest organic compounds contain only the elements carbon and hydrogen and are called hydrocarbons. Even though they are composed of only 2 types of atoms, there is a wide variety of hydrocarbons because they may consist of varying lengths of chains, branched chains, and rings of carbon atoms, or combinations of these structures. In addition, hydrocarbons may differ in the types of carbon-carbon bonds present in their molecules. Many hydrocarbons are found in plants, animals, and their fossils. Other hydrocarbons have been prepared in the laboratory. We use hydrocarbons every day, mainly as fuels, such as natural gas, acetylene, propane, butane, and the principal components of gasoline, diesel fuel, and heating oil. The familiar plastics polyethylene, polypropylene, and polystyrene are also hydrocarbons. We can distinguish several types of hydrocarbons by differences in the bonding between carbon atoms. This leads to differences in geometries and in the hybridization of the carbon orbitals. Alkanes. Alkanes, or saturated hydrocarbons, contain only single covalent bonds between carbon atoms. Each of the carbon atoms in an alkane has sp3 hybrid orbitals and is bonded to 4 other atoms, each of which is either carbon or hydrogen. The Lewis structures and models of methane, ethane, and pentane are illustrated in Figure 20. 2 carbon chains are usually drawn as straight lines in Lewis structures, but one has to remember that Lewis structures are not intended to indicate the geometry of molecules. Notice that the carbon atoms in the structural models, the ball and stick and space-filling models, of the pentane molecule do not lie in a straight line. Because of the sp3 hybridization, the bond angles in carbon chains are close to 109.5 degrees, giving such chains in an alkane a zigzag shape. The structures of alkanes and other organic molecules may also be represented in a less detailed manner by condensed structural formulas, or simply condensed formulas, instead of the usual format for chemical formulas in which each element symbol appears just once. A condensed formula is written to suggest the bonding in the molecule. These formulas have the appearance of a Lewis structure from which most or all of the bond symbols have been removed. Condensed structural formulas for ethane and pentane are shown at the bottom of Figure 20. 2, and several additional examples are provided in the exercises at the end of this chapter. The figure illustrates 4 ways to represent molecules for molecules of methane, ethane, and pentane. In the first row of the figure, Lewis structural formulas show element symbols and bonds between atoms. Methane has a central C atom with 4 H atoms bonded to it. Ethane has a C atom with 3 H atoms bonded to it. The C atom is also bonded to another C atom with 3 H atoms bonded to it. Pentane has a C atom with 3 H atoms bonded to it. The C atom is bonded to another C atom with 2 H atoms bonded to it. The C atom is bonded to another C atom with 2 H atoms bonded to it. The C atom is bonded to another C atom with 2 H atoms bonded to it. The C atom is bonded to another C atom with 3 H atoms bonded to it. In the second row, ball and stick models are shown. In these representations, bonds are represented with sticks, and elements are represented with balls. Carbon atoms are black and hydrogen atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged and pushed together, without sticks to represent bonds. The molecule names and structural formulas are provided in the fourth row. Methane is named and represented with a condensed structural formula as CH subscript 4. Ethane is named and represented with 2 structural formulas, CH subscript 3, CH subscript 3, and C subscript 2H subscript 6. Pentane is named and represented as both CH subscript 3CH subscript 2CH subscript 2CH subscript 2CH subscript 3 and C subscript 5H subscript 12. Figure 20. 2 pictured are the Lewis structures, ball and stick models, and space-filling models for molecules of methane, ethane, and pentane. A common method used by organic chemists to simplify the drawings of larger molecules is to use a skeletal structure, also called a line-angle structure. In this type of structure, carbon atoms are not symbolized with a C, but represented by each end of a line or bend in a line. Hydrogen atoms are not drawn if they are attached to a carbon. Other atoms besides carbon and hydrogen are represented by their elemental symbols. Figure 20. 3 shows 3 different ways to draw the same structure. In this figure, a hydrocarbon molecule is shown in 3 ways. First, an expanded formula shows all individual carbon atoms, hydrogen atoms, and bonds in a branched hydrocarbon molecule. An initial C atom is bonded to 3 H atoms. The C atom is bonded to another C atom in the chain. This second C atom is bonded to one H atom and another C atom above the chain. The C atom bonded above the second C atom in the chain is bonded to 3 H atoms. The second C atom in the chain is bonded to a third C atom in the chain. This third C atom is bonded to an H atom and another C atom below the chain. This C atom is bonded to 2 H atoms and another C atom below the chain. This second C atom below the chain is bonded to 3 H atoms. The third C atom in the chain is bonded to a fourth C atom in the chain. The fourth C atom is bonded to two H atoms and a fifth C atom. The fifth C atom is bonded to two H atoms and a sixth C atom. The sixth C atom is bonded to three H atoms. Second, a condensed formula shows each carbon atom of the molecule in clusters with the hydrogen atoms bonded to it, leaving CH, CH subscript 2, and CH subscript 3 groups with bonds between them. The structure shows a CH subscript 3 group bonded to a CH group. The CH group is bonded above to a CH subscript 3 group. The CH group is also bonded to another CH group. This CH group is bonded to a CH subscript 2 group below and a CH subscript 3 group below that. This CH group is also bonded to a CH subscript 2 group, which is bonded to another CH subscript 2 group. This CH subscript 2 group is bonded to a final CH subscript 2 group. The final structure in the figure is a skeletal structure, which includes only line segments arranged to indicate the structure of the molecule. Figure 20. 3. The same structure can be represented three different ways: an expanded formula, a condensed formula, and a skeletal structure. Example 20. 1. Drawing skeletal structures. Draw the skeletal structures for these two molecules. Figure A shows a branched molecule with CH subscript 3 bonded to C with CH subscript 3 groups bonded both above and below it. To the right of the central C, a CH is bonded which has a CH subscript 3 group bonded above and to the right and below and to the right. Figure B shows a straight chain molecule composed of CH subscript 3CH subscript 2CH subscript 2CH subscript 2CH subscript 2CH subscript 2CH subscript 3. Solution: each carbon atom is converted into the end of a line or the place where lines intersect. All hydrogen atoms attached to the carbon atoms are left out of the structure, although we still need to recognize they are there. Figure A shows a branched skeleton structure that looks like a plus sign with line segments extending up and to the right and down, and to the left of the rightmost point of the plus sign. Figure B appears in a zigzag pattern made with 6 line segments. The segments rise, fall, rise, fall, rise, and fall, moving left to right across the figure. Check your learning. Draw the skeletal structures for these two molecules. Figure A shows 5 CH subscript 2 groups and 1 CH group bonded in a hexagonal ring. A CH subscript 3 group appears above and to the right of the ring, bonded to the ring on the CH group appearing at the upper right portion of the ring. In B, a straight chain molecule composed of CH subscript 3CH subscript 2CH subscript 2CH subscript 2CH subscript 3 is shown. Answer: in A hexagon with a vertex at the top is shown. The vertex just to the right has a line segment attached that extends up and to the right. In B, a zigzag pattern is shown in which line segments rise, fall, and rise, moving left to right. Example 22. Interpreting skeletal structures. Identify the chemical formula of the molecule represented here. This figure shows a pentagon with a vertex pointing right, from which a line segment extends that has 2 line segments attached at its right end, one extending up and to the right, and the other extending down and to the right. Solution: there are 8 places where lines intersect or end, meaning that there are 8 carbon atoms in the molecule. Since we know that carbon atoms tend to make 4 bonds, each carbon atom will have the number of hydrogen atoms that are required for 4 bonds. This compound contains 16 hydrogen atoms for a molecular formula of C8H16. Location of the hydrogen atoms. In this figure, a ring composed of 4 CH subscript 2 groups and 1 CH group in a pentagonal shape is shown. From the CH group, which is at the right side of the pentagon, a CH is bonded. From this CH, a CH subscript 3 group is bonded above and to the right, and a second is bonded below and to the right. Check your learning. Identify the chemical formula of the molecule represented here. A skeleton model is shown with a zigzag pattern that rises, and falls again, left to right through the center of the molecule. From the 2 risen points, line segments extend both up and down, creating 4 branches. Answer: C9H20. All alkanes are composed of carbon and hydrogen atoms and have similar bonds, structures, and formulas. Non-cyclic alkanes all have a formula of CnH2n plus 2. The number of carbon atoms present in an alkane has no limit. Greater numbers of atoms in the molecules will lead to stronger intermolecular attractions, dispersion forces, and correspondingly different physical properties of the molecules. Properties such as melting point and boiling point, Table 21, usually change smoothly and predictably as the number of carbon and hydrogen atoms in the molecules change. Properties of some alkanes 3. Alkane molecular formula melting point, degrees C, boiling point, degrees C, phase at SDP 4 number of structural isomers. Methane CH4, 182. 5 161, 5 gas 1. Ethane C2H6, 183 388, 6 gas 1. Propane C3H8, 187, 742. 1 gas 1. Butane C4H10, 138, 305 gas 2. Pentane C5H12, 129, 736. 1 liquid 3. Hexane C6H14, 95, 368, 7 liquid 5. Heptane C7H16, 90, 698, 4 liquid 9. Octane C8H18, 56, 8 125, 7 liquid 18. Nonane C9H20, 53, 6 150, 8 liquid 35. Decane C10H22, 29, 7 174, 0 liquid 75. Tetraidecane C14H35, 9 253, 5 solid 1858. Octadecane C18H3828, 2 316, 1 solid 60, 523. Table 20, 1. Hydrocarbons with the same formula, including alkanes, can have different structures. For example, 2 alkanes have the formula C4H10. They are called N-butane and 2-methylpropane, or isobutane, and have the following Lewis structures. The figure illustrates 3 ways to represent molecules of N-butane and 2-methylpropane. In the first row of the figure, Lewis structural formulas show element symbols and bonds between atoms. The N-butane molecule shows 4 carbon atoms represented by the letter C bonded in a straight horizontal chain, with hydrogen atoms represented by the letter H bonded above and below all carbon atoms. H atoms are bonded at the ends to the left and right of the leftmost and rightmost C atoms. In the second row, ball and stick models are shown. In these representations, bonds are represented with sticks, and elements are represented with balls. Carbon atoms are black and hydrogen atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged and pushed together, without sticks to represent bonds. The molecule names are provided in the fourth row. The compounds N-butane and 2-methylpropane are structural isomers. The term constitutional isomers is also commonly used. Constitutional isomers have the same molecular formula, but different spatial arrangements of the atoms in their molecules. The N-butane molecule contains an unbranched chain, meaning that no carbon atom is bonded to more than 2 other carbon atoms. We use the term normal or the prefix N to refer to a chain of carbon atoms without branching. The compound 2-methylpropane has a branched chain. The carbon atom in the center of the Lewis structure is bonded to 3 other carbon atoms. Identifying isomers from Lewis structures is not as easy as it looks. Lewis structures that look different may actually represent the same isomers. For example, the 3 structures in Figure 20. 4 all represent the same molecule, N-butane, and hence are not different isomers. They are identical because each contains an unbranched chain of 4 carbon atoms. The figure illustrates 3 ways to represent molecules of N-butane. In the first row of the figure, Lewis structural formulas show carbon and hydrogen element symbols and bonds between the atoms. The first structure in this row shows 3 of the linked C atoms in a horizontal row with a single C atom bonded above the leftmost carbon. The leftmost C atom has 2 H atoms bonded to it. The C atom bonded above the leftmost C atom has 3 H atoms bonded to it. The C atom bonded to the right of the leftmost C atom has 2 H atoms bonded to it. The rightmost C atom has 3 H atoms bonded to it. The C atoms and the bonds connecting all the C atoms are red. The second structure in the row similarly shows the row of 3 linked C atoms with a single C atom bonded below the C atom to the left. The leftmost C atom has 2 H atoms bonded to it. The C atom bonded below the leftmost C atom has 3 H atoms bonded to it. The C atom bonded to the right of the leftmost C atom has 2 H atoms bonded to it. The rightmost atom has 3 H atoms bonded to it. All the C atoms and the bonds between them are red. The third structure has 2 C atoms bonded in a row with a third C atom bonded above the left C atom and the fourth C atom bonded below the right C atom. The C atom bonded above the left C atom has 3 H atoms bonded to it. The left C atom has 2 H atoms bonded to it. The right C atom has 2 H atoms bonded to it. The C atom bonded below the right C atom has 3 H atoms bonded to it. All the C atoms and the bonds between them are red. In the second row, ball and stick models for the structures are shown. In these representations, bonds are represented with sticks, and elements are represented with balls. Carbon atoms are black and hydrogen atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged and pushed together, without sticks to represent bonds. Figure 20. For these 3 representations of the structure of N-butane are not isomers because they all contain the same arrangement of atoms and bonds. The basics of organic nomenclature, naming alkanes. The International Union of Pure and Applied Chemistry, IUPAC, has devised a system of nomenclature that begins with the names of the alkanes and can be adjusted from there to account for more complicated structures. The nomenclature for alkanes is based on 2 rules. To name an alkane, first identify the longest chain of carbon atoms in its structure. A 2-carbon chain is called ethane, a 3-carbon chain, propane, and a 4-carbon chain, butane. Longer chains are named as follows: pentane 5-carbon chain, hexane 6, heptane 7, octane 8, nonane 9, and decane 10. These prefixes can be seen in the names of the alkanes described in Table 20. 1. Add prefixes to the name of the longest chain to indicate the positions and names of substituents. Substituents are branches or functional groups that replace hydrogen atoms on a chain. The position of a substituent or branch is identified by the number of the carbon atom it is bonded to in the chain. We number the carbon atoms in the chain by counting from the end of the chain nearest the substituents. Multiple substituents are named individually and placed in alphabetical order at the front of the name. This figure shows structural formulas for propane: 2-chloropropane, 2-methylpropane, 2,4-difluorohexane, and 1-bromo-3-chlorohexane. In each of the structures, the carbon atoms are in a row with bonded halogen atoms and a methyl group bonded below the figures. Propane is listed as simply CH subscript 3 CH subscript 2 CH subscript 3, with the numbers 1, 2, and 3 appearing above the carbon atoms from left to right. 2-chloropropane similarly shows CH subscript 3 CH subscript 3, with the numbers 1, 2, and 3 appearing above the carbon atoms from left to right. A Cl atom is bonded below carbon 2. The Cl atom is red. 2-methylpropane similarly shows CH subscript 3 CH subscript 3, with the numbers 3, 2, and 1 appearing above the carbon atoms from left to right. A CH subscript 3 group is bonded beneath carbon 2 and is red. 2,4-difluorohexane similarly shows CH subscript 3 CH subscript 2 CH subscript 2 CH subscript 3, with the numbers 6, 5, 4, 3, 2, and 1 appearing above the carbon atoms from left to right. F atoms are bonded to carbons 4 and 2 at the bottom of the structure and are red. 1-bromo-3-chlorohexane similarly shows CH subscript 2 CH subscript 2 CH subscript 2 CH subscript 2 CH subscript 3, with numbers 1, 2, 3, 4, 5, and 6 appearing above the carbon atoms from left to right. Br is bonded below carbon 1 and Cl is bonded below carbon 3. Both Br and Cl are red. When more than one substituent is present, either on the same carbon atom or on different carbon atoms, the substituents are listed alphabetically. Because the carbon atom numbering begins at the end closest to a substituent, the longest chain of carbon atoms is numbered in such a way as to produce the lowest number for the substituents. The ending O replaces "-ide at the end of the name of an electronegative substituent. In ionic compounds, the negatively charged ion ends with "-ide like chloride. In organic compounds, such atoms are treated as substituents and the O ending is used. The number of substituents of the same type is indicated by the prefixes D2, tri, 3, tetra 4, and so on. For example, difluoro indicates 2 fluoride substituents. Example 23. Naming halogen-substituted alkanes. Name the molecule whose structure is shown here. This structure shows a C atom bonded to the H atoms and another C atom. This second C atom is bonded to 2 H atoms and another C atom. This third C atom is bonded to a Br atom, an H atom, and another C atom. This fourth C atom is bonded to 2 H atoms and a Cl atom. Solution. This structure shows a C atom bonded to the H atoms and another C atom. This second C atom is bonded to 2 H atoms and another C atom. This third C atom is bonded to an H atom, a Br atom, and another C atom. This fourth C atom is bonded to 2 H atoms and a Cl atom. The C atoms are numbered 4, 3, 2, and 1 from left to right. The 4-carbon chain is numbered from the end with the chlorine atom. This puts the substituents on positions 1 and 2. Numbering from the other end would put the substituents on positions 3 and 4. 4 carbon atoms means that the base name of this compound will be butane. The bromine at position 2 will be described by adding 2 bromo. This will come at the beginning of the name, since bromo comes before chloro alphabetically. The chlorine at position 1 will be described by adding 1 chloro, resulting in the name of the molecule being 2-bromo-1-chlorobutane. Check your learning. Name the following molecule. This figure shows a C atom bonded to 3 H atoms and another C atom. This second C atom is bonded to 2 H atoms and a third C atom. The third C atom is bonded to 2 Br atoms and a fourth C atom. This C atom is bonded to an H atom, an I atom, and a fifth C atom. This last C atom is bonded to 3 H atoms. Answer: 3,3-bromo-2-iodopentane. We call a substituent that contains 1 less hydrogen than the corresponding alkane an alkyl group. The name of an alkyl group is obtained by dropping the suffix -ane of the alkane name and adding -il. In this figure, methane is named and represented as C with 4 H atoms bonded above, below, to the left, and to the right of the C the methyl group is shown, which appears like methane without the rightmost H. A dash remains at the location where the H was formerly bonded. Ethane is named and represented with 2 centrally bonded C atoms to which 6 H atoms are bonded, 2 above and below each of the 2 C atoms, and to the left and right ends of the linked C atoms. The ethyl group appears as a similar structure with the rightmost H atom removed. A dash remains at the location where the H atom was formerly bonded. The open bonds in the methyl and ethyl groups indicate that these alkyl groups are bonded to another atom. Example 24. Naming substituted alkanes. Name the molecule whose structure is shown here. A chain of 6 carbon atoms, numbered 6, 5, 4, 3, 2, and 1 is shown. Bonded above carbon 3, a chain of 2 carbons is shown, numbered 1 and 2 moving upward. H atoms are present directly above, below, left and right of all carbon atoms in positions not already taken up in bonding to other carbon atoms. Solution. The longest carbon chain runs horizontally across the page and contains 6 carbon atoms. This makes the base of the name hexane, but we will also need to incorporate the name of the branch. In this case, we want a number from right to left, as shown by the blue numbers. So the branch is connected to carbon 3. Imagine the numbers from left to right. This would put the branch on carbon 4, violating our rules. The branch attached to position 3 of our chain contains 2 carbon atoms, numbered in red. So we take our name for 2 carbons eth and attach -il at the end to signify we are describing a branch. Putting all the pieces together, this molecule is 3-ethylhexane. Check your learning. Name the following molecule. This figure shows a C atom bonded to 3 H atoms and another C atom. This C atom is bonded to 2 H atoms and third C atom. The third C atom is bonded to 2 H atoms and a fourth C atom. The fourth C atom is bonded to 2 H atoms and a fifth C atom. This C atom is bonded to an H atom, a sixth C atom in the chain, and another C atom which appears to branch off the chain. The C atom in the branch is bonded to two H atoms and another C atom. This C atom is bonded to two H atoms and another C atom. This third C atom appears to the left of the second and is bonded to three H atoms. The sixth C atom in the chain is bonded to two H atoms and a seventh C atom. The seventh C atom is bonded to two H atoms and an eighth C atom. The eighth C atom is bonded to three H atoms. Answer: 4-propyloctane. Some hydrocarbons can form more than one type of alkyl group when the hydrogen atoms that would be removed have different environments in the molecule. This diversity of possible alkyl groups can be identified in the following way. The four hydrogen atoms in a methane molecule are equivalent. They all have the same environment. They are equivalent because each is bonded to a carbon atom, the same carbon atom, that is bonded to three hydrogen atoms. It may be easier to see the equivalency in the ball and stick models in Figure 20. 2. Removal of any one of the four hydrogen atoms from methane forms a methyl group. Likewise, the six hydrogen atoms in ethane are equivalent, Figure 22, and removing any one of these hydrogen atoms produces an ethyl group. Each of the six hydrogen atoms is bonded to a carbon atom that is bonded to two other hydrogen atoms and a carbon atom. However, in both propane and 2-methylpropane, there are hydrogen atoms in two different environments, distinguished by the adjacent atoms or groups of atoms. In this figure, propane is shown as a chain of three bonded C atoms. 8 H atoms are shown with 3 bonded to the first C atom, 2 to the middle C atom, and 3 to the third C atom. The H atoms bonded to the middle C atom are purple. 2-methylpropane is also shown, which similarly has a chain of 3 bonded C atoms. In this structure, a C atom is bonded beneath the middle C atom of the chain. 10 H atoms are shown with 3 bonded to the first C atom, 1 to the middle C atom, 3 to the third C atom, and 3 to the C atom also bonded to the middle C atom. The H atom bonded to the middle C atom is green. Each of the 6 equivalent hydrogen atoms of the first type in propane and each of the 9 equivalent hydrogen atoms of that type in 2-methylpropane, all shown in black, are bonded to a carbon atom that is bonded to only one other carbon atom. The 2 purple hydrogen atoms in propane are of a second type. They differ from the 6 hydrogen atoms of the first type in that they are bonded to a carbon atom bonded to 2 other carbon atoms. The green hydrogen atom in 2-methylpropane differs from the other 9 hydrogen atoms in that molecule and from the purple hydrogen atoms in propane. The green hydrogen atom in 2-methylpropane is bonded to a carbon atom bonded to 3 other carbon atoms. 2 different alkyl groups can be formed from each of these molecules, depending on which hydrogen atom is removed. The names and structures of these and several other alkyl groups are listed in Figure 20. 5. This table provides a listing of alkyl groups and corresponding structures. Methyl is shown as CH subscript 3 followed by a dash. Ethyl is shown as CH subscript 3, CH subscript 2 followed by a dash. N-propyl is shown as CH subscript 3, CH subscript 2, CH subscript 2 followed by a dash. Isopropyl is shown as CH subscript 3, CH subscript 3 with a dash extending upward from the middle C. N-butyl is shown as CH subscript 3, CH subscript 2, CH subscript 2, CH subscript 2 followed by a dash. Sec-butyl is shown as CH subscript 3, CH subscript 2, CH subscript 3 with a dash extending upward from the third C counting left to right. Isobutyl is shown as CH subscript 3, CH subscript 2 with a dash extending to the right. There is a CH subscript 3 bonded to the middle C. Tert-butyl is shown as CH subscript 3, CH subscript 3 with a CH subscript 3 group bonded below the middle C, and a dash extending upward from the central C. Figure 20. 5. This listing gives the names and formulas for various alkyl groups formed by the removal of hydrogen atoms from different locations. Note that alkyl groups do not exist as stable independent entities. They are always a part of some larger molecule. The location of an alkyl group on a hydrocarbon chain is indicated in the same way as any other substituent. This figure shows structures of 3-ethylheptane, 2,2,4-trimethylpentane, and 4-isopropylheptane. The 3-ethylheptane structure shows CH subscript 3CH subscript 2CH subscript 2CH subscript 2CHCH subscript 2CH subscript 3. Under the C atom labeled 3 is a bond to CH subscript 2CH subscript 3, which appears in red. The C atoms are labeled 7, 6, 5, 4, 3, 2, and 1 from left to right. The 2,2,4-trimethylpentane structure shows CH subscript 3C bonded to CH subscript 2 CHCH subscript 3. The C atoms are labeled 1, 2, 3, 4, and 5 from left to right. The C atom labeled 2 has a CH subscript 3 bonded above it and below it. The CH subscript 3 groups both appear in red. The C atom labeled 4 has a bond above it to CH subscript 3. The CH subscript 3 group appears in red. The 4-isopropylheptane structure shows CH subscript 3CH subscript 2CH subscript 2CHCH subscript 2CH subscript 2CH subscript 3. From the fourth C counting from left to right, there is a CH group bonded above. Bonded up and to the right, and up to the left of this CH group are CH subscript 3 groups. Alkanes are relatively stable molecules, but heat or light will activate reactions that involve the breaking of CH or C single bonds. Combustion is one such reaction. CH4 letter 1D454 plus 2O2 letter 1D454 CO2 letter 1D454 plus 2H2O G. Alkanes burn in the presence of oxygen, a highly exothermic oxidation reduction reaction that produces carbon dioxide and water. As a consequence, alkanes are excellent fuels. For example, methane, CH4, is the principal component of natural gas. Butane, C4H10, used in camping stoves and lighters, is an alkane. Gasoline is a liquid mixture of continuous and branch-chain alkanes, each containing from 5 to 9 carbon atoms, plus various additives to improve its performance as a fuel. Kerosene, diesel oil, and fuel oil are primarily mixtures of alkanes with higher molecular masses. The main source of these liquid alkane fuels is crude oil, a complex mixture that is separated by fractional distillation. Fractional distillation takes advantage of differences in the boiling points of the components of the mixture, see Figure 20. 6. You may recall that boiling point is a function of intermolecular interactions, which was discussed in the chapter on solutions and colloids. This figure contains a photo of a refinery showing large columnar structures. A diagram of a fractional distillation column is also shown. Near the bottom of the column, an arrow pointing into the column from the left shows a point of entry for heated crude oil. The column contains several layers at which different components are removed. At the very bottom, residue materials are removed through a pipe as indicated by an arrow out of the column. At each successive level, different materials are removed through pipes proceeding from the bottom to the top of the column. In order from bottom to top, these materials are fuel oil, followed by diesel oil, kerosene, naphtha, gasoline, and refinery gas at the very top. To the right of the column diagram, a double-sided arrow is shown that is blue at the top and gradually changes color to red moving downward. The blue top of the arrow is labeled small molecules. Low boiling point, very volatile, flows easily, ignites easily. The red bottom of the arrow is labeled large molecules. High boiling point, not very volatile, does not flow easily, does not ignite easily. Figure 20. 6 in a column for the fractional distillation of crude oil. Oil heated to about 425 degrees C in the furnace vaporizes when it enters the base of the tower. The vapors rise through bubble caps in a series of trays in the tower. As the vapors gradually cool, fractions of higher, then of lower, boiling points condense to liquids and are drawn off. Credit left. Modification of work by Luigi Chiesa. In a substitution reaction, another typical reaction of alkanes, one or more of the alkane's hydrogen atoms is replaced with a different atom or group of atoms. No carbon-carbon bonds are broken in these reactions, and the hybridization of the carbon atoms does not change. For example, the reaction between ethane and molecular chlorine depicted here is a substitution reaction. This diagram illustrates the reaction of ethane and Cl subscript 2 to form chloroethane. In this reaction, the structural formula of ethane is shown with 2 C atoms bonded together and 3 H atoms bonded to each C atom. The H atom on the far right is red. Ethane is added to Cl bonded to Cl, followed by an arrow that points right. The arrow is labeled heat or light. To the right, the chloroethane molecule is shown with 2 C atoms bonded together. The left C atom has 3 H atoms bonded to it, but the right C atom has 2 H atoms bonded above and below it, along with a Cl atom. The Cl atom appears in red with 3 pairs of electron dots at the right end of the molecule. This is followed by a plus sign, which in turn is followed in red by H, bonded to Cl. 3 pairs of electron dots are present above, to the right, and below the Cl. The Cl portion of the chloroethane molecule is an example of a functional group, the part or moiety of a molecule that imparts a specific chemical reactivity. The types of functional groups present in an organic molecule are major determinants of its chemical properties and are used as a means of classifying organic compounds as detailed in the remaining sections of this chapter. Link to learning. Want more practice naming alkanes? Watch this brief video tutorial to review the nomenclature process. Alkenes, organic compounds that contain one or more double or triple bonds between carbon atoms, are described as unsaturated. You have likely heard of unsaturated fats. These are complex organic molecules with long chains of carbon atoms, which contain at least one double bond between carbon atoms. Unsaturated hydrocarbon molecules that contain one or more double bonds are called alkenes. Carbon atoms linked by a double bond are bound together by 2 bonds, 1 sigma bond and 1 pi bond. Double and triple bonds give rise to a different geometry around the carbon atom that participates in them, leading to important differences in molecular shape and properties. The differing geometries are responsible for the different properties of unsaturated versus saturated fats. Ethene, C2H4, is the simplest alkene. Each carbon atom in ethene, commonly called ethylene, has a trigonal planar structure. The second member of the series is propene, propylene, figure 27. The butene isomers follow in the series. 4 carbon atoms in the chain of butene allows for the formation of isomers based on the position of the double bond, as well as a new form of isomerism. Lewis structural formulas show carbon and hydrogen element symbols and bonds between the atoms. The first structure in this row shows 2 bonded C atoms with a double bond between them. Each C atom has 2 H atoms bonded to it as well. The second structure in the row shows 3 bonded C atoms with a double bond up and to the right between the first and second C atoms moving left to right across the chain, and a single bond down and to the right between the second and third C atom. The first C atom has 2 H atoms bonded to it, the second C atom has 1 H atom bonded to it, and the third C atom has 3 H atoms bonded to it. The third structure shows 4 bonded C atoms with 1 bonded up and to the right to a C atom, down and to the right to a C atom, and double bonded up and to the right to a C atom. The first C atom, moving from left to right, has 3 H atoms bonded to it. The second C atom has 2 H atoms bonded to it. The third C atom has 1 H atom bonded to it, and the fourth C atom has 2 H atoms bonded to it. In the second row, ball and stick models for the structures are shown. In these representations, single bonds are represented with sticks, double bonds are represented with 2 parallel sticks, and elements are represented with balls. Carbon atoms are black and hydrogen atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged and pushed together, without sticks to represent bonds. In the final row, names are provided. The molecule with the double bond between 2 C atoms is named ethene. The molecule with the double bond between the first and second C atoms in the chain of 3 is named propene. The molecule with the double bond between the carbon atoms in the chain of 4 is named 1-butene. Figure 20. 7 expanded structures, ball and stick structures, and space-filling models for the alkenes ethene, propene, and 1-butene are shown. Ethylene, the common industrial name for ethene, is a basic raw material in the production of polyethylene and other important compounds. Over 135 million tons of ethylene were produced worldwide in 2010 for use in the polymer, petrochemical, and plastic industries. Ethylene is produced industrially in a process called cracking, in which the long hydrocarbon chains in a petroleum mixture are broken into smaller molecules. Chemistry in everyday life. Recycling plastics. Polymers, from Greek words poly meaning many and mer meaning parts, are large molecules made up of repeating units, referred to as monomers. Polymers can be natural. Starch is a polymer of sugar residues and proteins are polymers of amino acids, or synthetic like polyethylene, polyvinyl chloride (PVC), and polystyrene. The variety of structures of polymers translates into a broad range of properties and uses that make them integral parts of our everyday lives. Adding functional groups to the structure of a polymer can result in significantly different properties. See the discussion about Kevlar later in this chapter. An example of a polymerization reaction is shown in Figure 20. 8. The monomer ethylene, C2H4, is a gas at room temperature, but when polymerized, using a transition metal catalyst, it is transformed into a solid material made up of long chains of CH2 units called polyethylene. Polyethylene is a commodity plastic used primarily for packaging bags and films. This diagram has 3 rows showing ethylene reacting to form polyethylene. In the first row, Lewis structural formulas show 3 molecules of ethylene being added together, which are each composed of 2 doubly bonded C atoms, each with 2 bonded H atoms. Ellipses, or 3 dots, are present before and after the molecule structures, which in turn are followed by an arrow pointing right. On the right side of the arrow, the ellipses or dots again appear to the left of a dash that connects to a chain of 7 C atoms, each with H atoms connected above and below. A dash appears at the end of the chain, which in turn is followed by ellipses or dots. The reaction diagram is repeated in the second row using ball and stick models for the structures. In these representations, single bonds are represented with sticks, double bonds are represented with 2 parallel sticks, and elements are represented with balls. Carbon atoms are black and hydrogen atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged spheres which are pushed together, without sticks to represent bonds. Figure 20. 8. The reaction for the polymerization of ethylene to polyethylene is shown. Polyethylene is a member of one subset of synthetic polymers classified as plastics. Plastics are synthetic organic solids that can be molded. They are typically organic polymers with high molecular masses. Most of the monomers that go into common plastics, ethylene, propylene, vinyl chloride, styrene, and ethylene terephthalate, are derived from petrochemicals and are not very biodegradable, making them candidate materials for recycling. Recycling plastics helps minimize the need for using more of the petrochemical supplies and also minimizes the environmental damage caused by throwing away these non-biodegradable materials. Plastic recycling is the process of recovering waste, scrap, or used plastics and reprocessing the material into useful products. For example, polyethylene terephthalate soft drink bottles can be melted down and used for plastic furniture, in carpets, or for other applications. Other plastics, like polyethylene bags and polypropylene cups, plastic food containers, can be recycled or reprocessed to be used again. Many areas of the country have recycling programs that focus on one or more of the commodity plastics that have been assigned a recycling code. See Figure 20. 9. These operations have been in effect since the 1970s and have made the production of some plastics among the most efficient industrial operations today. This table shows recycling symbols, names, and uses of various types of plastics. Symbols are shown with 3 arrows in a triangular shape surrounding a number. Number 1 is labeled PETE. The related plastic, polyethylene terephthalate, PETE, is used in soda bottles and oven-ready food trays. Number 2 is labeled HDPE. The related plastic is high-density polyethylene, HDPE, which is used in bottles for milk and dishwashing liquids. Number 3 is labeled V. The related plastic is polyvinyl chloride, or PVC. This plastic is used in food trays, plastic wrap, and bottles for mineral water and shampoo. Number 4 is labeled LDPE. This plastic is low-density polyethylene, LDPE. It is used in shopping bags and garbage bags. Number 5 is labeled PP. The related plastic is polypropylene, PP. It is used in margarine tubs and microwavable food trays. Number 6 is labeled PS. The related plastic is polystyrene, PS. It is used in yogurt tubs, foam meat trays, egg cartons, vending cups, plastic cutlery, and packaging for electronics and toys. Number 7 is labeled Other for any other plastics. Items in this category include those plastic materials that do not fit any other category. Melamine used in plastic plates and cups is an example. Figure 20. 9. Each type of recyclable plastic is imprinted with a code for easy identification. The name of an alkene is derived from the name of the alkane with the same number of carbon atoms. The presence of the double bond is signified by replacing the suffix -ane with the suffix -ene. The location of the double bond is identified by naming the smaller of the numbers of the carbon atoms participating in the double bond. 4 structural formulas and names are shown. The first shows 2 red C atoms connected by a red double bond illustrated with 2 parallel line segments. H atoms are bonded above and below to the left of the leftmost C atom. 2 more H atoms are similarly bonded to the right of the C atom on the right. Beneath this structure, the name ethene and alternate name ethylene are shown. The second shows 3 C atoms bonded together with a red double bond between the red first and second C atoms, moving left to right across the 3-carbon chain. H atoms are bonded above and below to the left of the C atom to the left. A single H is bonded above the middle C atom. 3 more H atoms are bonded above, below, and to the right of the third C atom. Beneath this structure, the name propene and alternate name propylene is shown. The third shows 4 C atoms bonded together, numbered 1 through 4 moving left to right with a red double bond between the red first and second carbon in the chain. H atoms are bonded above and below to the left of the C atom to the left. A single H is bonded above the second C atom. H atoms are bonded above and below the third C atom. 3 more H atoms are bonded above, below, and to the right of the fourth C atom. Beneath this structure, the name 1-butene is shown. The fourth shows 4 C atoms bonded together, numbered 1 through 4 moving left to right with a red double bond between the red second and third C atoms in the chain. H atoms are bonded above, below, and to the left of the leftmost C atom. A single H atom is bonded above the second C atom. A single H atom is bonded above the third C atom. 3 more H atoms are bonded above, below, and to the right of the fourth C atom. Beneath this structure, the name 2-butene is shown. Isomers of alkenes. Molecules of 1-butene and 2-butene are structural isomers. The arrangement of the atoms in these 2 molecules differs. As an example of arrangement differences, the first carbon atom in 1-butene is bonded to 2 hydrogen atoms. The first carbon atom in 2-butene is bonded to 3 hydrogen atoms. The compound 2-butene and some other alkenes also form a second type of isomer called a geometric isomer. In a set of geometric isomers, the same types of atoms are attached to each other in the same order, but the geometries of the 2 molecules differ. Geometric isomers of alkenes differ in the orientation of the groups on either side of a C equals C. Bond. Carbon atoms are free to rotate around a single bond, but not around a double bond. A double bond is rigid. This makes it possible to have 2 isomers of 2-butene, one with both methyl groups on the same side of the double bond and one with the methyl groups on opposite sides. When structures of butene are drawn with 120 degrees bond angles around the sp, 2 hybridized carbon atoms participating in the double bond, the isomers are apparent. The 2-butene isomer in which the 2 methyl groups are on the same side is called a cis-isomer. The one in which the 2 methyl groups are on opposite sides is called a transisomer, figure 20. 10. The different geometries produce different physical properties, such as boiling point, that may make separation of the isomers possible. The figure illustrates 3 ways to represent isomers of butene. In the first row of the figure, Lewis structural formulas show carbon and hydrogen element symbols and bonds between the atoms. The first structure in this row shows a C atom with a double bond to another C atom which is bonded down, and to the right to CH subscript 2 which, in turn, is bonded to CH subscript 3. The first C atom, moving from left to right, has two H atoms bonded to it, and the second C atom has one H atom bonded to it. The second structure in the row shows a C atom with a double bond to another C atom. The first C atom is bonded to an H atom up and to the left, and CH subscript 3 down and to the left. The second C atom is bonded to an H atom up and to the right, and CH subscript 3 down and to the right. Both CH subscript 3 structures appear in red. The third structure shows a C atom with a double bond to another C atom. The first C atom from the left is bonded up to the left to CH subscript 3, which appears in red. It is also bonded down and to the left to an H atom. The second C atom is bonded up and to the right to an H atom, and down and to the left to CH subscript 3, which appears in red. In the second row, ball and stick models for the structures are shown. In these representations, single bonds are represented with sticks, double bonds are represented with two parallel sticks, and elements are represented with balls. C atoms are black and H atoms are white in this image. In the third row, space-filling models are shown. In these models, atoms are enlarged and pushed together without sticks to represent bonds. In the final row, names are provided. The molecule with the double bond between the first and second carbons is named 1-butene. The two molecules with the double bond between the second and third carbon atoms is called 2-butene. The first model, which has both CH subscript 3 groups beneath the double bond, is called the cis isomer. The second, which has the CH subscript 3 groups on opposite sides of the double bond, is named the trans isomer. Figure 20. 10. These molecular models show the structural and geometric isomers of butene. Alkenes are much more reactive than alkanes because the C equals C. Moiety is a reactive functional group. A pi bond, being a weaker bond, is disrupted much more easily than a sigma bond. Thus, alkenes undergo a characteristic reaction in which the pi bond is broken and replaced by two sigma bonds. This reaction is called an addition reaction. The hybridization of the carbon atoms in the double bond in an alkene changes from sp2 to sp3 during an addition reaction. For example, halogens add to the double bond in an alkene instead of replacing hydrogen, as occurs in an alkane. This diagram illustrates the reaction of ethene and Cl subscript 2 to form 1,2-dichloroethane. In this reaction, the structural formula of ethane is shown. It has a double bond between the two C atoms, with two H atoms bonded to each C atom, plus Cl bonded to Cl. This is shown on to the left of an arrow. The two C atoms and the double bond between them are shown in red. To the right of the arrow, the 1,2-dichloroethane molecule is shown. It has only single bonds, and each C atom has a Cl with 3 pairs of electron dots bonded beneath it. The C and Cl atoms, single bond between them, and electron pairs are shown in red. Each C atom also has two H atoms bonded to it. Example 20. 5. Alkene reactivity and naming. Provide the IUPAC names for the reactant and product of the halogenation reaction shown here. The left side of a reaction and arrow are shown with an empty product side. On the left, CH subscript 3 is bonded down, and to the right to CH, which has a double bond to another CH, the second CH is bonded up. And to the right to CH subscript 2, which is also bonded to CH subscript 3. A plus sign is shown with a Cl atom bonded to a Cl atom following it. This is also followed by a reaction arrow. Solution. The reactant is a 5-carbon chain that contains a carbon-carbon double bond, so the base name will be pentene. We begin counting at the end of the chain closest to the double bond, in this case, from the left. The double bond spans carbons 2 and 3, so the name becomes 2-pentene. Since there are two carbon-containing groups attached to the two carbon atoms in the double bond, and they are on the same side of the double bond, this molecule is the cis isomer, making the name of the starting alkene cis-2-pentene. The product of the halogenation reaction will have two chlorine atoms attached to the carbon atoms that were a part of the carbon-carbon double bond. CH subscript 3 is bonded down, and to the right to CH, which is bonded down, and to the left to Cl. CH is also bonded to another CH, which is bonded down, and to the right to Cl and up, and to the right to CH subscript 2. CH subscript 2 is also bonded to CH subscript 3. This molecule is now a substituted alkane and will be named as such. The base of the name will be pentane. We will count from the end that numbers the carbon atoms where the chlorine atoms are attached as 2 and 3, making the name of the product 2,3-dichloropentane. Check your learning. Provide names for the reactant and product of the reaction shown. This shows a C atom bonded to 3 H atoms and another C atom. This second C atom is bonded to 2 H atoms and a third C atom. This third C atom is bonded to 1 H atom and also forms a double bond with a fourth C atom. This fourth C atom is bonded to 1 H atom and a fifth C atom. This fifth C atom is bonded to 2 H atoms and a sixth C atom. This sixth C atom is bonded to 3 H atoms. There is a plus sign followed by a Cl atom bonded to another Cl atom. There is a reaction arrow. No products are shown. Answer: reactant, cis-3-hexene product, 3,4-dichlorohexane. Alkanes. Hydrocarbon molecules with one or more triple bonds are called alkanes. They make up another series of unsaturated hydrocarbons. Two carbon atoms joined by a triple bond are bound together by 1 sigma bond and 2 pi bonds. The sp hybridized carbons involved in the triple bond have bond angles of 180 degrees, giving these types of bonds a linear, rod-like shape. The simplest member of the alkane series is ethyne, C2H2, commonly called acetylene. The Lewis structure for ethyne, a linear molecule, is. The structural formula and name for ethyne, also known as acetylene, are shown. In red, 2 C atoms are shown with a triple bond illustrated by 3 horizontal line segments between them. Shown in black at each end of the structure, a single H atom is bonded. The IUPAC nomenclature for alkynes is similar to that for alkenes, except that the suffix -un is used to indicate a triple bond in the chain. For example, CH3CH to C, identical to CH, is called 1-butane. Example 26. Structure of alkanes. Describe the geometry and hybridization of the carbon atoms in the following molecule. A structural formula is shown with CH subscript 3, bonded to a C atom, which is triple bonded to another C atom, which is bonded to CH subscript 3. Each C atom is labeled 1, 2, 3, and 4 from left to right. Solution. Carbon atoms 1 and 4 have 4 single bonds and are thus tetrahedral with sp3 hybridization. Carbon atoms 2 and 3 are involved in the triple bond, so they have linear geometries and would be classified as sp hybrids. Check your learning. Identify the hybridization and bond angles at the carbon atoms in the molecule shown. A structural formula is shown with an H atom bonded to a C atom. The C atom has a triple bond with another C atom, which is also bonded to CH. The CH has a double bond with another CH, which is also bonded up and to the right to CH subscript 3. Each C atom is labeled 1, 2, 3, 4, or 5 from left to right. Answer: carbon 1, sp 180 degrees, carbon 2, sp 180 degrees, carbon 3, sp2 120 degrees, carbon 4, sp2 120 degrees, carbon 5, sp3 109, 5 degrees. Chemically, the alkynes are similar to the alkenes, since the C identical to C. Functional group has 2 pi bonds. Alkynes typically react even more readily and react with twice as much reagent in addition reactions. The reaction of acetylene with bromine is a typical example. This diagram illustrates the reaction of ethyne and 2 molecules of Br subscript 2 to form 1, 1, 2, 2 tetrabromothane. In this reaction, the structural formula of ethyne, an H atom bonded to a red C atom with a red triple bond to another red C atom bonded to a black H atom, plus Br bonded to Br plus Br bonded to Br is shown to the left of an arrow. On the right, the form 1, 1, 2, 2 tetrabromothane molecule is shown. It has an H atom bonded to a C atom, which is bonded to another C atom, which is bonded to an H atom. Each C atom is bonded above and below to a Br atom. Each Br atom has 3 pairs of electron dots. The C and Br atoms single bond between them, and electron pairs are shown in red. Acetylene and the other alkynes also burn readily. An acetylene torch takes advantage of the high heat of combustion for acetylene. Aromatic hydrocarbons. Benzene, C6H6, is the simplest member of a large family of hydrocarbons, called aromatic hydrocarbons. These compounds contain ring structures and exhibit bonding that must be described using the resonance hybrid concept of valence bond theory or the delocalization concept of molecular orbital theory. To review these concepts, refer to the earlier chapters on chemical bonding. The resonance structures for benzene, C6H6, are: this structural formula shows a 6-carbon hydrocarbon ring. On the left side, there are 6 C atoms. The C atom on top and to the left forms a single bond to the C atom on the top and to the right. The C atom has a double bond to another C atom, which has a single bond to a C atom. That C atom has a double bond to another C atom, which has a single bond to a C atom. That C atom forms a double bond with another C atom. Each C atom has a single bond to an H atom. There is a double-sided arrow, and the structure on the right is almost identical to the structure on the left. The structure on the right shows double bonds, where the structure on the left showed single bonds. The structure on the right shows single bonds, where the structure on the left showed double bonds. Valence bond theory describes the benzene molecule and other planar aromatic hydrocarbon molecules as hexagonal rings of sp2 hybridized carbon atoms with the unhybridized p orbital of each carbon atom perpendicular to the plane of the ring. 3 valence electrons in the sp2 hybrid orbitals of each carbon atom and the valence electron of each hydrogen atom form the framework of sigma bonds in the benzene molecule. The 4th valence electron of each carbon atom is shared with an adjacent carbon atom in their unhybridized p orbitals to yield the pi bonds. Benzene does not, however, exhibit the characteristics typical of an alkene. Each of the 6 bonds between its carbon atoms is equivalent and exhibits properties that are intermediate between those of a C single bond, and a C equals C double bond. To represent this unique bonding, structural formulas for benzene and its derivatives are typically drawn with single bonds between the carbon atoms and a circle within the ring as shown in Figure 20. 11. A 6-carbon hydrocarbon ring structural formula is shown. Each C atom is bonded to only one H atom. A circle is at the center of the ring. Figure 20. 11. This condensed formula shows the unique bonding structure of benzene. There are many derivatives of benzene. The hydrogen atoms can be replaced by many different substituents. Aromatic compounds more readily undergo substitution reactions than addition reactions. Replacement of one of the hydrogen atoms with another substituent will leave the delocalized double bonds intact. The following are typical examples of substituted benzene derivatives. 3 structural formulas are shown. The first is labeled toluene. This molecule has a 6-carbon hydrocarbon ring in which 5 of the C atoms are each bonded to only one H atom. At the upper right of the ring, the C atom that does not have a bonded H atom has a red CH subscript 3 group attached. A circle is at the center of the ring. The second is labeled xylene. This molecule has a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. At the upper right and right of the ring, the 2 C atoms that do not have bonded H atoms have CH subscript 3 groups attached. These CH subscript 3 groups appear in red. A circle is at the center of the ring. The third is labeled styrene. This molecule has a 6-carbon hydrocarbon ring in which 5 of the carbon atoms are each bonded to only one H atom. At the upper right of the ring, the carbon that does not have a bonded H atom has a red CH double bond CH subscript 2 group attached. A circle is at the center of the ring. Toluene and xylene are important solvents and raw materials in the chemical industry. Styrene is used to produce the polymer polystyrene. Example 20. 7. Structure of aromatic hydrocarbons. One possible isomer, created by a substitution reaction, that replaces a hydrogen atom attached to the aromatic ring of toluene with a chlorine atom is shown here. Draw 2 other possible isomers in which the chlorine atom replaces a different hydrogen atom attached to the aromatic ring. two structural formulas are shown. The first has a 6-carbon hydrocarbon ring in which 4 of the carbon atoms are each bonded to only one H atom. At the upper right of the ring, the carbon that does not have a bonded H atom has a CH subscript 3 group attached. The C to the lower right has a Cl atom attached. A circle is at the center of the ring. The second molecule has a hexagon with a circle inside. From a vertex of the hexagon at the upper right, a CH subscript 3 group is attached. From the vertex at the lower right, a Cl atom is attached. Solution. Since the 6-carbon ring with alternating double bonds is necessary for the molecule to be classified as aromatic, appropriate isomers, can be produced only by changing the positions of the chlorosubstituent relative to the methyl substituent. 2 pairs of structural formulas are shown. The first has a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. At the upper right of the ring, the C atom that does not have a bonded H atom has a CH subscript 3 group attached. The C atom to the right has a Cl atom attached. A circle is at the center of the ring. The second molecule in the first pair has a hexagon with a circle inside. From a vertex of the hexagon at the upper right, a CH subscript 3 group is attached. From the vertex at the right, a Cl atom is attached. The second pair first shows a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. A Cl atom is attached to the leftmost C atom, and a CH subscript 3 group is attached to the rightmost C atom. A circle is at the center of the ring. The second molecule in the pair has a hexagon with a circle inside. A CH subscript 3 group is attached to a vertex on the right side of the hexagon, and to a vertex on the left side, a Cl atom is bonded. Check your learning. Draw 3 isomers of a 6-membered aromatic ring compound substituted with 2 bromines. Answer. 3 pairs of structural formulas are shown. The first has a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. At the upper right and right of the ring, the 2 C atoms that do not have bonded H atoms have one Br atom bonded each. A circle is at the center of the ring. Beneath this structure, a similar structure is shown which has a hexagon with a circle inside. From vertices of the hexagon at the upper right and right, single Br atoms are attached. The second has a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. At the upper right and lower right of the ring, the 2 C atoms that do not have bonded H atoms have a single Br atom bonded each. A circle is at the center of the ring. Beneath this structure, a similar structure is shown which has a hexagon with a circle inside. From vertices of the hexagon at the upper right and lower right, single Br atoms are attached. The third has a 6-carbon hydrocarbon ring in which 4 of the C atoms are each bonded to only one H atom. At the upper right and lower left of the ring, the 2 C atoms that do not have bonded H atoms have Br atoms bonded. A circle is at the center of the ring. Beneath this structure, a similar structure is shown which has a hexagon with a circle inside. From vertices of the hexagon at the upper right and lower left, single Br atoms are attached. Learning objectives. By the end of this section, you will be able to describe the structure and properties of alcohols, describe the structure and properties of ethers, name and draw structures for alcohols and ethers. In this section, we will learn about alcohols and ethers. Alcohols, incorporation of an oxygen atom into carbon and hydrogen-containing molecules, leads to new functional groups and new families of compounds. When the oxygen atom is attached by single bonds, the molecule is either an alcohol or ether. Alcohols are derivatives of hydrocarbons in which an OH group has replaced a hydrogen atom. Although all alcohols have one or more hydroxyl, OH, functional groups, they do not behave like bases such as NaOH and KOH. NaOH and KOH are ionic compounds that contain OH ions. Alcohols are covalent molecules. The OH group in an alcohol molecule is attached to a carbon atom by a covalent bond. Ethanol, CH3CH2OH, also called ethyl alcohol, is a particularly important alcohol for human use. Ethanol is the alcohol produced by some species of yeast that is found in wine, beer, and distilled drinks. It has long been prepared by humans harnessing the metabolic efforts of yeasts in fermenting various sugars. This figure shows the reaction of glucose to produce ethanol and CO subscript 2. The reaction shows C subscript 6H subscript 12O subscript 6. A Q arrow labeled yeast 2C subscript 2H subscript 5OH, a Q plus 2CO subscript 2, G. The OH in ethanol is shown in red. Large quantities of ethanol are synthesized from the addition reaction of water with ethylene using an acid as a catalyst. This reaction shows two carbons connected by a double bond, each with two bonded H atoms plus HOH arrow labeled H subscript 3O superscript plus, followed by two carbon atoms connected with a single bond with 5 bonded H atoms and an OH group shown in red at the right end of the molecule. The O of this group is shown with 2 pairs of electron dots. Alcohols containing 2 or more hydroxyl groups can be made. Examples include 12-ethane-diol ethylene glycol, used in antifreeze, and 1,2,3-propanetriol glycerine, used as a solvent for cosmetics and medicines. Structural formulas for 1,2-ethane-diol and 1,2,3-propanetriol are shown. The first structure has a 2C atom hydrocarbon chain with an OH group attached to each carbon. The OH groups are shown in red, and each O atom has 2 sets of electron dots. Each C atom also has 2 H atoms bonded to it. The second structure shows a 3C atom hydrocarbon chain with an OH group bonded to each carbon. The OH groups are shown in red, and each O atom has 2 sets of electron dots. The first C atom has 2 H atoms bonded to it. The second C atom has 1 H atom bonded to it. The third C atom has 2 H atoms bonded to it. Naming alcohols. The name of an alcohol comes from the hydrocarbon from which it was derived. The final E in the name of the hydrocarbon is replaced by -ol, and the carbon atom to which the OH group is bonded is indicated by a number placed before the name. 5. Example 28. Naming alcohols. Consider the following example. How should it be named? A molecular structure of a hydrocarbon chain with a length of 5 C atoms is shown. The first C atom, from left to right, is bonded to 3 H atoms. The second C atom is bonded on 1 H atom and an O atom which is also bonded to an H atom. The O atom has 2 sets of electron dots. The third C atom is bonded to 2 H atoms. The fourth C atom is bonded to 2 H atoms. The fifth C atom is bonded to 3 H atoms. All bonds shown are single. Solution. The carbon chain contains 5 carbon atoms. If the hydroxyl group was not present, we would have named this molecule pentane. To address the fact that the hydroxyl group is present, we change the ending of the name to -ol. In this case, since the OH is attached to carbon 2 in the chain, we would name this molecule 2-pentanol. Check your learning. Name the following molecule. The structure shown has a CH subscript 3 group bonded up and to the right to a C atom. The C atom is bonded down and to the right to a CH subscript 2 group. The CH subscript 2 group is bonded up and to the right to a CH subscript 2 group. The CH subscript 2 group is bonded down and to the right to a CH subscript 3 group. The second C atom, from left to right, is bonded to a CH subscript 3 group and an OH group. Answer. 2-methyl-2-pentanol. Ethers. Ethers are compounds that contain the functional group O. Ethers do not have a designated suffix like the other types of molecules we have named so far. In the IUPAC system, the oxygen atom and the smaller carbon branch are named as an alkoxy substituent, and the remainder of the molecule as the base chain, as in alkanes. As shown in the following compound, the red symbols represent the smaller alkyl group and the oxygen atom, which would be named methoxy. The larger carbon branch would be ethane, making the molecule methoxyethane. Many ethers are referred to with common names instead of the IUPAC system names. For common names, the 2 branches connected to the oxygen atom are named separately and followed by ether. The common name for the compound shown in example 29 is ethylmethyl ether. A molecular structure is shown with a red CH subscript 3 group bonded up and to the right to a red O atom. The O atom is bonded down and to the right to a CH subscript 2 group. The CH subscript 2 group is bonded up and to the right to a CH subscript 3 group. Example 20. 9. Naming ethers. Provide the IUPAC and common name for the ether shown here. A molecular structure shows a CH subscript 3 group bonded down and to the right to a CH subscript 2 group. The CH subscript 2 group is bonded up and to the right to an O atom. The O atom is bonded down and to the right to a CH subscript 2 group. The CH subscript 2 group is bonded up and to the right to a CH subscript 3 group. Solution. IUPAC. The molecule is made up of an ethoxy group attached to an ethane chain, so the IUPAC name would be ethoxyethane. Common. The groups attached to the oxygen atom are both ethyl groups, so the common name would be diethyl ether. Check your learning. Provide the IUPAC and common name for the ether shown. A molecular structure shows a CH subscript 3 group bonded up and to the right to an O atom. The O atom is bonded down and to the right to a CH group. The CH group is bonded up and to the right to a CH subscript 3 group. The CH group is also bonded down and to the right to another CH subscript 3 group. Answer IUPAC. 2-methoxypropane, common, isopropyl methyl ether. Ethers can be obtained from alcohols by the elimination of a molecule of water from 2 molecules of the alcohol. For example, when ethanol is treated with a limited amount of sulfuric acid and heated to 140 degrees C, diethyl ether and water are formed. This figure shows a reaction. The first molecule, which is labeled ethanol, is a 2C atom chain. The first C atom is bonded to 3 H atoms and a second C atom. The second C atom is bonded to a red O atom with 2 sets of electron dots. The O atom has a red bond to a red H atom. There is a plus sign. The next molecule, which is labeled ethanol, is a red H atom with a red bond to a red O atom with 2 pairs of electron dots. The O atom is bonded to a C atom, which is bonded to 2 H atoms and a second C atom. The second C atom is bonded to 3 H atoms. There is a green dotted box around the red H atom in the first molecule, the plus sign, and the red H and O atoms in the second molecule. To the right of the second molecule, there is an arrow labeled H subscript 2 SO subscript 4 above and Greek capital delta below. The arrow is labeled sulfuric acid. The resulting molecules are a C atom bonded with 3 H atoms and a second C atom. The second C atom is bonded to 2 H atoms and a red O atom. The red O atom has 2 sets of electron dots. The O atom is bonded to a third C atom, which is bonded to 2 H atoms and a fourth C atom. The fourth C atom is bonded to 3 H atoms. This molecule is labeled diethyl ether. There is a plus sign and a red HOH in the general formula for ethers, R, O, R. The hydrocarbon groups, R, may be the same or different. Diethyl ether, the most widely used compound of this class, is a colorless, volatile liquid that is highly flammable. It was first used in 1846 as an anesthetic, but better anesthetics have now largely taken its place. Diethyl ether and other ethers are presently used primarily as solvents for gums, fats, waxes, and resins. Tertiary butyl methyl ether, C4H9OCH3, abbreviated MTBE, italicized portions of names are not counted when ranking the groups alphabetically, so butyl comes before methyl in the common name, is used as an additive for gasoline. MTBE belongs to a group of chemicals known as oxygenates due to their capacity to increase the oxygen content of gasoline. Link to learning. Want more practice naming ethers? This brief video review summarizes the nomenclature for ethers. Chemistry in everyday life. Carbohydrates and diabetes. Carbohydrates are large biomolecules made up of carbon, hydrogen, and oxygen. The dietary forms of carbohydrates are foods rich in these types of molecules, like pastas, bread, and candy. The name carbohydrate comes from the formula of the molecules, which can be described by the general formula CMHON, which shows that they are in a sense carbon and water, or hydrates of carbon. In many cases, M and N have the same value, but they can be different. The smaller carbohydrates are generally referred to as sugars. The biochemical term for this group of molecules is saccharide from the Greek word for sugar, figure 20. 12. Depending on the number of sugar units joined together, they may be classified as monosaccharides, 1 sugar unit, disaccharides, 2 sugar units, oligosaccharides, a few sugars, or polysaccharides, the polymeric version of sugars. Polymers were described in the feature box earlier in this chapter on recycling plastics. The scientific names of sugars can be recognized by the suffix -ose at the end of the name. For instance, fruit sugar is a monosaccharide called fructose, and milk sugar is a disaccharide called lactose, composed of 2 monosaccharides, glucose and galactose, connected together. Sugars contain some of the functional groups we have discussed. Note the alcohol groups present in the structures and how monosaccharide units are linked to form a disaccharide by formation of an ether. This figure shows structural and ball-and-stick models for the common sugars fructose and lactose. Carbon atoms are illustrated in black, oxygen atoms are red, and hydrogen atoms are white in the ball-and-stick models. Figure 20. 12. The illustrations show the molecular structures of fructose, a 5-carbon monosaccharide, and of lactose, a disaccharide composed of 2 isomeric, 6-carbon sugars. Organisms use carbohydrates for a variety of functions. Carbohydrates can store energy, such as the polysaccharides glycogen in animals or starch in plants. They also provide structural support, such as the polysaccharide cellulose in plants and the modified polysaccharide chitin in fungi and animals. The sugars ribose and deoxyribose are components of the backbones of RNA and DNA, respectively. Other sugars play key roles in the function of the immune system, in cell-cell recognition, and in many other biological roles. Diabetes is a group of metabolic diseases in which a person has a high sugar concentration in their blood, figure 20. 13. Diabetes may be caused by insufficient insulin production by the pancreas or by the body's cells not responding properly to the insulin that is produced. In a healthy person, insulin is produced when it is needed and functions to transport glucose from the blood into the cells where it can be used for energy. The long-term complications of diabetes can include loss of eyesight, heart disease, and kidney failure. In 2013, it was estimated that approximately 3% of the world's population, 380 million people, suffered from diabetes, resulting in over 1 million deaths annually. Prevention involves eating a healthy diet, getting plenty of exercise, and maintaining a normal body weight. Treatment involves all of these lifestyle practices and may require injections of insulin. Even after treatment protocols were introduced, the need to continually monitor their glucose levels posed a challenge for people with diabetes. The first tests required a doctor or lab and therefore limited access and frequency. Eventually, researchers developed small tablets that would react to the presence of glucose in urine, but these still required a relatively complex process. Chemist Helen Free, who was working on improvements to the tablets, conceived a simpler device, a small test strip. With her husband and research partner, Alfred Free, she produced the first such product for measuring glucose. Soon after, she expanded the technology to provide test strips for other compounds and conditions. While very recent advances, such as breath tests, discussed earlier in the text, have shown promise in replacing test strips, they have been widely used for decades and remain a primary method today. This is a diagram of a hand with a blood droplet on an index finger and a nearby sharp, pointed pen-like object. The finger is next shown touching a white and green test strip with arrows pointing to the green region where the bloody finger touches the strip. An arrow points to a small rectangular device in which the green end of the strip is inserted. An LCD display provides a reading. Figure 20. 13. Diabetes is a disease characterized by high concentrations of glucose in the blood. Treating diabetes involves making lifestyle changes, monitoring blood sugar levels, and sometimes insulin injections. Credit: Blosson Medical Communications / Wikimedia Commons. Learning objectives. By the end of this section, you will be able to describe the structure and properties of aldehydes, ketones, carboxylic acids, and esters. Another class of organic molecules contains a carbon atom connected to an oxygen atom by a double bond, commonly called a carbonyl group. The trigonal planar carbon in the carbonyl group can attach to 2 other substituents leading to several subfamilies. Aldehydes, ketones, carboxylic acids, and esters described in this section. Aldehydes and ketones. Both aldehydes and ketones contain a carbonyl group, a functional group with a carbon-oxygen double bond. The names for aldehyde and ketone compounds are derived using similar nomenclature rules as for alkanes and alcohols, and include the class-identifying suffixes -al and -one, respectively. A C atom is shown with dashes appearing to the left and right. An O atom is double bonded above the C atom. In an aldehyde, the carbonyl group is bonded to at least one hydrogen atom. In a ketone, the carbonyl group is bonded to 2 carbon atoms. 5 structures are shown. The first is a C atom with an R group bonded to the left and an H atom to the right. An O atom is double bonded above the C atom. This structure is labeled functional group of an aldehyde. The second structure shows a C atom with R groups bonded to the left and right. An O atom is double bonded above the C atom. This structure is labeled functional group of a ketone. The third structure looks exactly like the functional group of a ketone. The fourth structure is labeled CH subscript 3CHO. It is also labeled an aldehyde and ethinyl acetaldehyde. This structure has a C atom to which 3 H atoms are bonded above, below, and to the left. In red to the right of this C atom, a C atom is attached which has an O atom double bonded above and an H atom bonded to the right. The O atom has 2 sets of electron dots. The fifth structure is labeled CH subscript 3COCH subscript 2CH subscript 3. It is also labeled a ketone and butanone. This structure has a C atom to which 3 H atoms are bonded above, below, and to the left. To the right of this in red is a C atom to which an O atom is double bonded above. The O atom has 2 sets of electron dots. Attached to the right of this red C atom in black is a 2-carbon atom chain with H atoms attached above, below, and to the right. No alt text. As text, an aldehyde group is represented as CHO. A ketone is represented as C, O, or CO. In both aldehydes and ketones, the geometry around the carbon atom in the carbonyl group is trigonal planar. The carbon atom exhibits sp2 hybridization. 2 of the sp2 orbitals on the carbon atom in the carbonyl group are used to form sigma bonds to the other carbon or hydrogen atoms in a molecule. The remaining sp2 hybrid orbital forms a sigma bond to the oxygen atom. The unhybridized p orbital on the carbon atom in the carbonyl group overlaps a p orbital on the oxygen atom to form the pi bond in the double bond. Like the C equals O bond in carbon dioxide, the C equals O bond of a carbonyl group is polar. Recall that oxygen is significantly more electronegative than carbon, and the shared electrons are pulled toward the oxygen atom and away from the carbon atom. Many of the reactions of aldehydes and ketones start with the reaction between a Lewis base and the carbon atom at the positive end of the polar C equals O bond to yield an unstable intermediate that subsequently undergoes one or more structural rearrangements to form the final product. Figure 20. 14. This structure shows a central C atom to which an O atom is double bonded above. To the lower left, R superscript 1 is bonded, and to the lower right, R superscript 2 is bonded. A Greek lowercase delta superscript plus appears to the left of the C and just above the bond with R superscript 1. Similarly, a Greek lowercase delta superscript negative sign appears to the left of the O atom. An arc is drawn from the double bond that links the C atom and the O atom to the bond that links the C atom to the R superscript 2 group. This arc is labeled approximately 120 degrees. Figure 20. 14. The carbonyl group is polar, and the geometry of the bonds around the central carbon is trigonal planar. The importance of molecular structure in the reactivity of organic compounds is illustrated by the reactions that produce aldehydes and ketones. We can prepare a carbonyl group by oxidation of an alcohol. For organic molecules, oxidation of a carbon atom is said to occur when a carbon-hydrogen bond is replaced by a carbon-oxygen bond. The reverse reaction, replacing a carbon-oxygen bond by a carbon-hydrogen bond, is a reduction of that carbon atom. Recall that oxygen is generally assigned a 2 oxidation number unless it is elemental or attached to a fluorine. Hydrogen is generally assigned an oxidation number of +1 unless it is attached to a metal. Since carbon does not have a specific rule, Its oxidation number is determined algebraically by factoring the atoms it is attached to and the overall charge of the molecule or ion. In general, a carbon atom attached to an oxygen atom will have a more positive oxidation number, and a carbon atom attached to a hydrogen atom will have a more negative oxidation number. This should fit nicely with your understanding of the polarity of C, O, and C, H bonds. The other reagents and possible products of these reactions are beyond the scope of this chapter, so we will focus only on the changes to the carbon atoms. A reaction is shown. On the left appears an alcohol, and on the right, a carbonyl group. Above the reaction arrow appears the word oxidation. The alcohol is represented as a C atom with dashes to the left and below, an H atom bonded above, and an O atom bonded to an H atom in red connected to the right. The O atom has two sets of electron dots. The carbonyl group is indicated in red with a C atom to which an O atom is double bonded above. Dashes appear left and right of the C atom in black. The O atom has two sets of electron dots. Example 20, 10. Oxidation and reduction in organic chemistry. Methane represents the completely reduced form of an organic molecule that contains one carbon atom. Sequentially replacing each of the carbon-hydrogen bonds with a carbon-oxygen bond would lead to an alcohol, then an aldehyde, then a carboxylic acid, discussed later. And, finally, carbon dioxide. CH4CH3, OCH2OHCOH. What are the oxidation numbers for the carbon atoms in the molecules shown here? Solution. In this example, we can calculate the oxidation number, review the chapter on oxidation-reduction reactions, if necessary, for the carbon atom in each case. Note how this would become difficult for larger molecules with additional carbon atoms and hydrogen atoms, which is why organic chemists use the definition dealing with replacing C, H bonds with C, O bonds described. For CH4, the carbon atom carries a 4 oxidation number. The hydrogen atoms are assigned oxidation numbers of +1, and the carbon atom balances that by having an oxidation number of 4. For the alcohol, in this case methanol, the carbon atom has an oxidation number of 2. The oxygen atom is assigned 2, the 4 hydrogen atoms each are assigned +1, and the carbon atom balances the sum by having an oxidation number of 2. Note that compared to the carbon atom in CH4, this carbon atom has lost 2 electrons, so it was oxidized. For the aldehyde, the carbon atom's oxidation number is 0. 2 for the oxygen atom, and +1 for each hydrogen atom already balances to 0, so the oxidation number for the carbon atom is 0. For the carboxylic acid, the carbon atom's oxidation number is +2, 2 oxygen atoms each at 2 and 2 hydrogen atoms at +1. And for carbon dioxide, the carbon atom's oxidation number is +4. Here, the carbon atom needs to balance the 4 sum from the 2 oxygen atoms. Check your learning. Indicate whether the marked carbon atoms in the 3 molecules here are oxidized or reduced relative to the marked carbon atom in ethanol. A molecular structure is shown. A CH subscript 3 group is bonded up and to the right to a CH subscript 2 group. Bonded to the CH subscript 2 group down, and to the right is an OH group. There is no need to calculate oxidation states in this case. Instead, just compare the types of atoms bonded to the marked carbon atoms. 3 molecular structures are shown, each with a red central C atom. In a CH subscript 3 group is bonded to the lower left, an H atom is bonded above, and H subscript 2 appears to the right of the central C atom. In B, an O atom is double bonded above the central C atom. A CH subscript 3 group is bonded to the lower left, and an H atom is bonded to the lower right. In C, an O atom is double bonded above the central C atom. A CH subscript 3 group is bonded to the lower left, and an OH group is bonded to the lower right. Answer. A. Reduced, bond to oxygen atom replaced by bond to hydrogen atom. B. Oxidized, 1 bond to hydrogen atom replaced by 1 bond to oxygen atom. C. Oxidized, 2 bonds to hydrogen atoms have been replaced by bonds to an oxygen atom. Aldehydes are commonly prepared by the oxidation of alcohols whose O functional group is located on the carbon atom at the end of the chain of carbon atoms in the alcohol. A reaction is shown. An alcohol appears on the left and an aldehyde on the right of the reaction arrow. The alcohol is shown as CH subscript 3CH subscript 2CH subscript 2OH, and the aldehyde is shown as CH subscript 3CH subscript 2CHO. The OH group at the right end of the alcohol structure and the CHO group at the right end of the aldehyde structure are in red. Alcohols that have their O groups in the middle of the chain are necessary to synthesize a ketone, which requires the carbonyl group to be bonded to two other carbon atoms. A reaction is shown. An alcohol appears on the left and a ketone on the right of the reaction arrow. The alcohol is shown as CH subscript 3CH, OH, CH subscript 3, and the ketone is shown as CH subscript 3COCH subscript 3. The OH group in the alcohol structure and the CO group at the center of the ketone structure are in red. An alcohol with its OH group bonded to a carbon atom that is bonded to no or one other carbon atom will form an aldehyde. An alcohol with its OH group attached to two other carbon atoms will form a ketone. If 3 carbons are attached to the carbon bonded to the OH, the molecule will not have a C-H bond to be replaced, so it will not be susceptible to oxidation. Formaldehyde, an aldehyde with the formula HCHO, is a colorless gas with a pungent and irritating odor. It is sold in an aqueous solution called formalin, which contains about 37% formaldehyde by weight. Formaldehyde causes coagulation of proteins, so it kills bacteria and any other living organism, and stops many of the biological processes that cause tissue to decay. Thus, formaldehyde is used for preserving tissue specimens and embalming bodies. It is also used to sterilize soil or other materials. Formaldehyde is used in the manufacture of bakelite, a hard plastic having high chemical and electrical resistance. Dimethyl ketone, CH3COCH3, commonly called acetone, is the simplest ketone. It is made commercially by fermenting corn or molasses or by oxidation of 2-propanol. Acetone is a colorless liquid. Among its many uses are as a solvent for lacquer, including fingernail polish, cellulose acetate, cellulose nitrate, acetylene, plastics, and varnishes, as a paint and varnish remover, and as a solvent in the manufacture of pharmaceuticals and chemicals, carboxylic acids and esters. The odor of vinegar is caused by the presence of acetic acid, a carboxylic acid, in the vinegar. The odor of ripe bananas and many other fruits is due to the presence of esters, compounds that can be prepared by the reaction of a carboxylic acid with an alcohol. Because esters do not have hydrogen bonds between molecules, they have lower vapor pressures than the alcohols and carboxylic acids from which they are derived. See Figure 2015. There are 9 structures represented in this figure. The first is labeled raspberry and isobutyl formate. It shows an H atom with a line going up and to the right, which then goes down and to the right. It goes up and to the right again and down and to the right and up and to the right. At the first peak is a double bond to an O atom. At the first trough is an O atom. At the second trough, there is a line going straight down. The second is labeled apple and butyl acetate. There is a line that goes up and to the right, down and to the right, up and to the right, and down and to the right. At the second peak is a double bond to an O atom. At the end on the right is OCH subscript 3. The third is labeled pineapple and ethyl butyrate. It is a line that goes up and to the right, down and to the right, up and to the right, down and to the right, up and to the right, and down and to the right. At the second peak is a double bond to an O atom, and at the second trough is an O atom. The fourth is labeled rum and propyl isobutyrate. It shows a line that goes down and to the right, up and to the right, down and to the right, up and to the right, down and to the right, and up and to the right. The first complete peak has a double bond to an O atom, and the second trough has an O atom. The fifth is labeled peach and benzyl acetate. It shows a line that goes up and to the right, down and to the right, up and to the right, and down and to the right. This line connects to a hexagon with a circle inside it. The first peak has a double bond to an O atom, and the first trough has an O atom. The sixth is labeled orange and octyl acetate. It shows a line that goes up and to the right and down, and to the right and up, and to the right and down, and to the right and up, and to the right and down, and to the right and up, and to the right and down, and to the right and up, and to the right and down, and to the right. The first peak has a double bond to an O atom, and the first complete trough has an O atom. The seventh is labeled wintergreen and methyl salicylate. It shows a hexagon with a circle inside of it. On the right is a bond down and to the right to an OH group. On the right is a bond to a line that goes up and to the right and down and to the right and up and to the right. At the first peak is a double bond to an O atom. The next trough shows an O atom, and at the end of the line is a CH subscript 3 group. The eighth is labeled honey and methyl phenylacetate. It shows a hexagon with a circle inside of it. It shows it connecting to a line on the right that goes down, and to the right then up and to the right and down, and to the right and up and to the right. At the first peak that is not part of the hexagon is a double bond to an O atom. At the last trough is an O atom. The ninth is labeled strawberry and ethyl methylphenylglycidate. This shows a hexagon with a circle inside of it. On the right, it connects to a line that goes up and to the right and down, and to the right and up, and to the right and down, and to the right and up, and to the right and down, and to the right. At the first peak is a line that extends above and below. Below, it connects to an O atom. At the next trough, the line extends down and to the left to the same O atom. At the next peak is a double bond to an O atom, and at the next trough is an O atom. Figure 20. 15 esters are responsible for the odors associated with various plants and their fruits. Both carboxylic acids and esters contain a carbonyl group with a second oxygen atom bonded to the carbon atom in the carbonyl group by a single bond. In a carboxylic acid, the second oxygen atom also bonds to a hydrogen atom. In an ester, the second oxygen atom bonds to another carbon atom. The names for carboxylic acids and esters include prefixes that denote the lengths of the carbon chains in the molecules and are derived following nomenclature rules similar to those for inorganic acids and salts. See these examples. Two structures are shown. The first structure is labeled ethanoic acid and acetic acid. This structure indicates a C atom to which H atoms are bonded above, below, and to the left. To the right of this in red is a bonded group comprised of a C atom to which an O atom is double bonded above. To the right of the red C atom, an O atom is bonded, which has an H atom bonded to its right. Both O atoms have two sets of electron dots. The second structure is labeled methyl ethanoate and methyl acetate. This structure indicates a C atom to which H atoms are bonded above, below, and to the left. In red, bonded to the right is a C atom with a double bonded O atom above and a single bonded O atom to the right. To the right of this last O atom in black is another C atom to which H atoms are bonded above, below, and to the right. Both O atoms have two pairs of electron dots. The functional groups for an acid and for an ester are shown in red in these formulas. The hydrogen atom in the functional group of a carboxylic acid will react with a base to form an ionic salt. A chemical reaction is shown. On the left, a structure of propionic acid is indicated. This structure includes a 2-carbon hydrocarbon group on the left end in black. Above, below, and to the left, H atoms are bonded. This group is bonded to a red group comprised of a C atom to which an O atom is double bonded above. To the right of the red C atom, an O atom is connected with a single bond. To the right of the O atom, an H atom is bonded. To the right of this structure appears a plus and NaOH following the reaction arrow. The propionate ion is shown. This structure is in brackets. Appearing inside the brackets is a 2-carbon hydrocarbon group on the left end. Above, below, and to the left, H atoms are bonded. To the right of this group, a group in red is attached comprised of a C atom to which an O atom is double bonded above, and a second O atom is single bonded to the right. Outside the brackets appears a superscript minus symbol. This is followed by a plus sign, and a superscript plus another plus sign, and H subscript 2, O. The singly bonded O atom in the propionate ion structure has 3 pairs of electron dots. All other O atoms have 2 pairs of electron dots. Carboxylic acids are weak acids, see the chapter on acids and bases, meaning they are not 100% ionized in water. Generally, only about 1% of the molecules of a carboxylic acid dissolved in water are ionized at any given time. The remaining molecules are undissociated in solution. We prepare carboxylic acids by the oxidation of aldehydes or alcohols, whose O functional group is located on the carbon atom at the end of the chain of carbon atoms in the alcohol. A chemical reaction with two arrows is shown. On the left, an alcohol, indicated with a C atom to which an R group is bonded to the left. H atoms are bonded above and below, and in red, a single bonded O atom with an H atom bonded to the right is shown. Following the first reaction arrow, an aldehyde is shown. This structure is represented with an R group bonded to a red C atom to which an H atom is bonded above and to the right, and an O atom is double bonded below and to the right. Appearing to the right of the second arrow is a carboxylic acid comprised of an R group bonded to a C atom to which, in red, an O atom is single bonded with an H atom bonded to its right side. A red O is double bonded below and to the right. All O atoms have two pairs of electron dots. Esters are produced by the reaction of acids with alcohols. For example, the ester ethyl acetate, CH3 to CH3, is formed when acetic acid reacts with ethanol. A chemical reaction is shown. On the left, a CH subscript 3 group bonded to a red C atom. The C atom forms a double bond with an O atom which is also in red. The C atom is also bonded to an O atom which is bonded to an H atom, also in red. A plus sign is shown, which is followed by HOCH subscript 2CH subscript 3. The HO group is in red. Following a reaction arrow, a CH subscript 3 group is shown, which is bonded to a red C atom with a double bonded O atom, and a single bonded O to the right of this single bonded O atom. A CH subscript 2CH subscript 3 group is attached and shown in black. This structure is followed by a plus sign, and H subscript 2 O the O atoms in the first structure on the left, and the structure following the reaction arrow have two pairs of electron dots. The simplest carboxylic acid is formic acid, HCO2H, known since 1670. Its name comes from the Latin word formicus, which means ant. It was first isolated by the distillation of red ants. It is partially responsible for the pain and irritation of ant and wasp stings, and is responsible for a characteristic odor of ants that can be sometimes detected in their nests. Acetic acid, CH3COH, constitutes 3,6% vinegar. Cider vinegar is produced by allowing apple juice to ferment without oxygen present. Yeast cells present in the juice carry out the fermentation reactions. The fermentation reactions change the sugar present in the juice to ethanol, then to acetic acid. Pure acetic acid has a penetrating odor and produces painful burns. It is an excellent solvent for many organic and some inorganic compounds, and it is essential in the production of cellulose acetate, a component of many synthetic fibers such as rayon. The distinctive and attractive odors and flavors of many flowers, perfumes, and ripe fruits are due to the presence of one or more esters, figure 20. 16. Among the most important of the natural esters are fats, such as lard, tallow and butter, and oils, such as linseed, cottonseed, and olive oils, which are esters of the trihydroxyl alcohol glycerine, C3H5O3, with large carboxylic acids, such as palmitic acid, CH3, CH214CO2H, stearic acid, CH3, CH216CO2H, and oleic acid, CH3CH2, 7CH equals CH, CH2 7CO2H. Oleic acid is an unsaturated acid. It contains a C equals C. Double bond. Palmitic and stearic acids are saturated acids that contain no double or triple bonds. This is a photo of a bright red strawberry being held in a human hand. Figure 20. 16 over 350 different volatile molecules, many members of the ester family, have been identified in strawberries. Credit: Rebecca Siegel. Learning objectives. By the end of this section, you will be able to describe the structure and properties of an amine. Describe the structure and properties of an amide. Amines are molecules that contain carbon-nitrogen bonds. The nitrogen atom in an amine has a lone pair of electrons and 3 bonds to other atoms, either carbon or hydrogen. Various nomenclatures are used to derive names for amines, but all involve the class-identifying suffix, -ine, as illustrated here for a few simple examples. 3 structures are shown, each with a red, central N atom which has a pair of electron dots indicated in red above the N atoms. The first structure is labeled methylamine. To the left of the N, a CH subscript 3 group is bonded. H atoms are bonded to the right and bottom of the central N atom. The second structure is labeled dimethylamine. This structure has CH subscript 3 groups bonded to the left and right of the N atom, and a single H atom is bonded below. The third structure is labeled trimethylamine, which has CH subscript 3 groups bonded to the left, right, and below the central N atom. In some amines, the nitrogen atom replaces a carbon atom in an aromatic hydrocarbon. Pyridine, figure 20. 17 is one such heterocyclic amine. A heterocyclic compound contains atoms of 2 or more different elements in its ring structure. A molecular structure is shown. A ring of 5 C atoms and 1 N atom is shown with alternating double bonds. Single H atoms are bonded, appearing at the outside of the ring on each C atom. The N atom has an unshared electron pair shown on the N atom on the outer side of the ring. The N atom, electron dot pair, and bonds connected to it in the ring are shown in red. Figure 20. 17, the illustration shows one of the resonance structures of pyridine. How sciences interconnect: DNA and forensics and paternity. The genetic material for all living things is a polymer of 4 different molecules, which are themselves a combination of 3 subunits. The genetic information, the code for developing an organism, is contained in the specific sequence of the 4 molecules, similar to the way the letters of the alphabet can be sequenced to form words that convey information. The information in a DNA sequence is used to form 2 other types of polymers, one of which are proteins. The proteins interact to form a specific type of organism with individual characteristics. A genetic molecule is called DNA, which stands for deoxyribonucleic acid. The 4 molecules that make up DNA are called nucleotides. Each nucleotide consists of a single or double-ringed molecule containing nitrogen, carbon, oxygen, and hydrogen called a nitrogenous base. Each base is bonded to a 5-carbon sugar called deoxyribose. The sugar is in turn bonded to a phosphate group, -PO43-. When new DNA is made, a polymerization reaction occurs that binds the phosphate group of one nucleotide to the sugar group of a second nucleotide. The nitrogenous bases of each nucleotide stick out from this sugar-phosphate backbone. DNA is actually formed from 2 such polymers coiled around each other and held together by hydrogen bonds between the nitrogenous bases. Thus, the 2 backbones are on the outside of the coiled pair of strands, and the bases are on the inside. The shape of the 2 strands wound around each other is called a double helix, see figure 20. 18. It probably makes sense that the sequence of nucleotides in the DNA of a cat differs from those of a dog. But it is also true that the sequences of the DNA in the cells of 2 individual pugs differ. Likewise, the sequences of DNA in you and a sibling differ, unless your sibling is an identical twin, as do those between you and an unrelated individual. However, the DNA sequences of 2 related individuals are more similar than the sequences of 2 unrelated individuals, and these similarities in sequence can be observed in various ways. This is the principle behind DNA fingerprinting, which is a method used to determine whether 2 DNA samples came from related or the same individuals or unrelated individuals. Diagram shows DNA as a double helix composed of the nitrogenous bases adenine, thymine, guanine, and cytosine paired up along a sugar-phosphate backbone. The helix has labeled 3' and 5' directions or ends. In diagram B, the molecular level arrangement of the bases connected by hydrogen bonding within the sugar-phosphate backbone is shown. Adenine is shown with hydrogen bonding to thymine, and similarly the linkage via hydrogen bonding between cytosine and guanine is shown. Again, 3' and 5' directional information is provided. In diagram C, the bonding between a nitrogenous base, sugar, and phosphate is shown. Figure 20. 18 DNA is an organic molecule and the genetic material for all living organisms. A DNA is a double helix consisting of 2 single DNA strands hydrogen bonded together at each nitrogenous base. B. This detail shows the hydrogen bonding, dotted lines, between nitrogenous bases on each DNA strand, and the way in which each nucleotide is joined to the next, forming a backbone of sugars and phosphate groups along each strand. See, this detail shows the structure of one of the 4 nucleotides that makes up the DNA polymer. Each nucleotide consists of a nitrogenous base, a double-ring molecule, in this case, a 5-carbon sugar deoxyribose, and a phosphate group. Using similarities in sequences, technicians can determine whether a man is the father of a child. The identity of the mother is rarely in doubt, except in the case of an adopted child and a potential birth mother. Likewise, forensic geneticists can determine whether a crime scene sample of human tissue, such as blood or skin cells, contains DNA that matches exactly the DNA of a suspect. Link to learning. Watch this video animation of how DNA is packaged for a visual lesson in its structure. Like ammonia, amines are weak bases due to the lone pair of electrons on their nitrogen atoms. 2 reactions are shown. In the first, ammonia reacts with H superscript plus. An unshared pair of electron dots sits above the N atom. To the left, right, and bottom, H atoms are bonded. This is followed by a plus symbol and an H atom with a superscript plus symbol. To the right of the reaction arrow, ammonium ion is shown in brackets with a superscript plus symbol outside. Inside the brackets, the N atom is shown with H atoms bonded on all 4 sides. In a very similar second reaction, methylamine reacts with H superscript plus to yield methylammonium ion. The methylamine structure is like ammonia, except a CH subscript 3 group is attached in place of the leftmost H atom in the structure. Similarly, the resulting methylammonium ion is represented in brackets with a superscript plus symbol appearing outside. Inside, the structure is similar to that of methylamine, except that an H atom appears at the top of the N atom, where the unshared electron pair was previously shown. The basicity of anamine's nitrogen atom plays an important role in much of the compound's chemistry. Amine functional groups are found in a wide variety of compounds, including natural and synthetic dyes, polymers, vitamins, and medications such as penicillin and codeine. They are also found in many molecules essential to life, such as amino acids, hormones, neurotransmitters, and DNA. How sciences interconnect. Addictive alkaloids. Since ancient times, plants have been used for medicinal purposes. One class of substances, called alkaloids, found in many of these plants has been isolated and found to contain cyclic molecules with an amine functional group. These amines are bases. They can react with H3O+ in a dilute acid to form an ammonium salt, and this property is used to extract them from the plant. R3N plus H3O++ Cl- R3NH plus Cl- plus H2O. The name alkaloid means like an alkali. Thus, an alkaloid reacts with acid. The free compound can be recovered after extraction by reaction with a base. R3NH plus Cl- plus O- R3N plus H2O plus Cl-. The structures of many naturally occurring alkaloids have profound physiological and psychotropic effects in humans. Examples of these drugs include nicotine, morphine, codeine, and heroin. The plant produces these substances, collectively called secondary plant compounds, as chemical defenses against the numerous pests that attempt to feed on the plant. Molecular structures of nicotine, morphine, codeine, and heroin are shown. These large structures share some common features, including rings. In the complex structures of morphine, codeine, and heroin, bonds to some O atoms in the structures are indicated with dashed wedges, and bonds to some H atoms and N atoms are shown as solid wedges. In these diagrams, as is common in representing structures of large organic compounds, carbon atoms in the rings and the hydrogen atoms bonded to them have been omitted for clarity. The solid wedges indicate bonds that extend out of the page. The dashed wedges indicate bonds that extend into the page. Notice that small changes to a part of the molecule change the properties of morphine, codeine, and heroin. Morphine, a strong narcotic used to relieve pain, contains 2 hydroxyl functional groups, located at the bottom of the molecule in this structural formula. Changing one of these hydroxyl groups to a methyl ether group forms codeine, a less potent drug used as a local anesthetic. If both hydroxyl groups are converted to esters of acetic acid, the powerfully addictive drug heroin results. Figure 20. 19. This is a photo of a field of red-orange poppies. Figure 20. 19 poppies can be used in the production of opium, a plant latex that contains morphine from which other opiates, such as heroin, can be synthesized. Credit Karen Rowe. Amides are molecules that contain nitrogen atoms connected to the carbon atom of a carbonyl group. Like amines, various nomenclature rules may be used to name amides, but all include use of the class-specific suffix amide. This figure shows 3 structures. 2 examples are provided. The basic structure has an H atom or R group bonded to a C atom which is double bonded to an O atom. The O atom has 2 sets of electron dots. The C atom is bonded to an N atom, which in turn is bonded to 2 R groups or 2 H atoms. The N atom has 1 set of electron dots. The next structure includes acetamide, which has CH subscript 3 bonded to a C atom with a doubly bonded O atom. The second C atom is also bonded to NH subscript 2. Hexanamide has a hydrocarbon chain of length 6 involving all single bonds. The condensed structure is shown here. To the 6th C atom at the right end of the chain, an O atom is double bonded, and an NH subscript 2 group is single bonded. Amides can be produced when carboxylic acids react with amines or ammonia in a process called imidation. A water molecule is eliminated from the reaction, and the amide is formed from the remaining pieces of the carboxylic acid and the amine. Note the similarity to formation of an ester from a carboxylic acid and an alcohol discussed in the previous section. A chemical reaction is shown between a carboxylic acid and amine to form an amide and water. Structures are shown. The carboxylic acid is shown as a CH subscript 3 group bonded to a CH subscript 2 group bonded to a C atom with a double bonded O atom above and an OH group bonded to the right. There is a plus sign. The amine is shown as an N atom with 2 H atoms bonded to the bottom and left sides. A CH subscript 3 group is bonded to the right side of the N atom. To the right of an arrow, an amide is shown as a CH subscript 3 group bonded to a CH subscript 2 group, bonded to a C atom which is double bonded to an O atom above, and an N with an H atom bonded below. The N atom is bonded to a CH subscript 3 group. The final product indicated after a plus sign is water. H subscript 2, O. The reaction between amines and carboxylic acids to form amides is biologically important. It is through this reaction that amino acids, molecules containing both amine and carboxylic acid substituents, link together in a polymer to form proteins. How sciences interconnect. Proteins and enzymes. Proteins are large biological molecules made up of long chains of smaller molecules called amino acids. Organisms rely on proteins for a variety of functions. Proteins transport molecules across cell membranes, replicate DNA, and catalyze metabolic reactions, to name only a few of their functions. The properties of proteins are functions of the combination of amino acids that compose them and can vary greatly. Interactions between amino acid sequences in the chains of proteins result in the folding of the chain into specific, three-dimensional structures that determine the protein's activity. Amino acids are organic molecules that contain an amine functional group, NH2, a carboxylic acid functional group, COOH, and a side chain that is specific to each individual amino acid. Most living things build proteins from the same 20 different amino acids. Amino acids connect by the formation of a peptide bond, which is a covalent bond formed between 2 amino acids when the carboxylic acid group of one amino acid reacts with the amine group of the other amino acid. The formation of the bond results in the production of a molecule of water. In general, reactions that result in the production of water when 2 other molecules combine are referred to as condensation reactions. The resulting bond between the carbonyl group carbon atom and the amine nitrogen atom is called a peptide link or peptide bond. Since each of the original amino acids has an unreacted group, one has an unreacted amine and the other an unreacted carboxylic acid, more peptide bonds can form to other amino acids, extending the structure. Figure 20. A chain of connected amino acids is called a polypeptide. Proteins contain at least one long polypeptide chain. This figure shows two amino acid molecules. These molecules have two singly bonded carbon atoms to which an amino group is bonded on the left, and the C atom to the right is a component of a carboxyl group. The C atom at the center has an R group bonded below and an H atom bonded above. The amino acid at the top left has an amino group identified and enclosed in a green dashed rectangle. This group is comprised of an N atom with two bonded H atoms. The amino acid at the right has a carboxyl group identified in a green dashed rectangle. This group has a C atom to which an OH group and a doubly bonded O atom are bonded. The amino acid to the left has the OH group to the lower right in red. The amino acid on the right has an H atom that is bonded to the N atom in red. An arrow points downward and is labeled condensation reaction. A curved arrow extends down and to the right off of the downward arrow, pointing to H subscript 2O, which is in red. A single, larger molecule appears beneath the downward arrow. At the locations of the red OH group and H atom, the amino acid molecules are bonded together. This bond is labeled as a peptide bond, and the larger molecule formed is labeled as a polypeptide chain. Figure 20. This condensation reaction forms a dipeptide from two amino acids and leads to the formation of water. Enzymes are large biological molecules, mostly composed of proteins, which are responsible for the thousands of metabolic processes that occur in living organisms. Enzymes are highly specific catalysts. They speed up the rates of certain reactions. Enzymes function by lowering the activation energy of the reaction they are catalyzing, which can dramatically increase the rate of the reaction. Most reactions catalyzed by enzymes have rates that are millions of times faster than the non-catalyzed version. Like all catalysts, enzymes are not consumed during the reactions that they catalyze. Enzymes do differ from other catalysts in how specific they are for their substrates, the molecules that an enzyme will convert into a different product. Each enzyme is only capable of speeding up one or a few very specific reactions or types of reactions. Since the function of enzymes is so specific, the lack or malfunctioning of an enzyme can lead to serious health consequences. One disease that is the result of an enzyme malfunction is phenylketonuria. In this disease, the enzyme that catalyzes the first step in the degradation of the amino acid phenylalanine is not functional, figure 20. 21. Untreated, this can lead to an accumulation of phenylalanine, which can lead to intellectual disabilities. This figure includes a computer-generated image of an enzyme molecule showing string and curled ribbon-like structural components in purple, green, and yellow hues. Figure 20. 21. A computer rendering shows the three-dimensional structure of the enzyme phenylalanine hydroxylase. In the disease phenylketonuria, a defect in the shape of phenylalanine hydroxylase causes it to lose its function in breaking down phenylalanine. Chemistry in everyday life. Kevlar figure 20. 22 is a synthetic polymer made from two monomers 1,4-phenylenediamine and terephthalate chloride. Kevlar is a registered trademark of DuPont. The material was developed by Stephanie Kwolek while she worked to find a replacement for steel in tires. Kwolek's work involved synthesizing polyamides and dissolving them in solvents, then spinning the resulting solution into fibers. One of her solutions proved to be quite different in initial appearance and structure, and once spun, the resulting fibers were particularly strong. From this initial discovery, Kevlar was created. The material has a high tensile strength-to-weight ratio. It is about 5 times stronger than an equal weight of steel, making it useful for many applications from bicycle tires to sails to body armor. A structural formula is shown for the polymer Kevlar. The structure appears inside brackets which have single dashes extending from them at the left and right ends. Outside the lower right corner of the brackets, an italicized N appears. The structure inside the brackets includes a C atom forming a double bond with an O atom and a bond with a benzene ring. The benzene ring forms a bond with another C atom, which has a double bond with an O atom. The C atom is bonded to an N atom. The N atom is bonded to an H atom and a benzene ring. The benzene ring bonds with another N atom, which is also bonded to an H atom. Figure 20. 22. This illustration shows the formula for polymeric Kevlar. The material owes much of its strength to hydrogen bonds between polymer chains. Refer back to the chapter on intermolecular interactions. These bonds form between the carbonyl group oxygen atom, which has a partial negative charge due to oxygen's electronegativity, on one monomer, and the partially positively charged hydrogen atom in the NH bond of an adjacent monomer in the polymer structure. See dashed line in Figure 20. 23. There is additional strength derived from the interaction between the unhybridized p orbitals in the six-membered rings, called aromatic stacking. This diagram shows the repeating, interlinked units that exist in Kevlar, taking on a sheet-like appearance. Dashed line segments are indicated between units. Individual units are composed of nitrogen, hydrogen, oxygen, and carbon atoms. The repeating structural units include benzene rings and double bonds. Figure 20. 23. The diagram shows the polymer structure of Kevlar, with hydrogen bonds between polymer chains represented by dotted lines. Kevlar may be best known as a component of body armor, combat helmets, and face masks. Since the 1980s, the U.S. military has used Kevlar as a component of the PASGT, Personal Armor System for ground troops, helmet and vest. Kevlar is also used to protect armored fighting vehicles and aircraft carriers. Civilian applications include protective gear for emergency service personnel, such as body armor for police officers and heat-resistant clothing for firefighters. Kevlar-based clothing is considerably lighter and thinner than equivalent gear made from other materials. Figure 20. 24. Beyond Kevlar, Stephanie Kwolek was instrumental in the development of Nomex, a fireproof material, and was also involved in the creation of Lycra. She became just the fourth woman inducted into the National Inventors Hall of Fame and received a number of other awards for her significant contributions to science and society. 3 photos are shown. In the first, 2 male soldiers are shown sorting through green-brown material on a table. In the second, 2 people are shown paddling a canoe. In the third, heavy white rope is being manipulated with a hand tool. Figure 20. 24a. These soldiers are sorting through pieces of a Kevlar helmet that helped absorb a grenade blast. Kevlar is also used to make B, canoes, and C, marine mooring lines. Credit A. Modification of work by Claw68/Wikimedia Commons. Credit B. Modification of work by Oakley Originals/Flickr. Credit C. Modification of work by Casey H. Kill. In addition to its better-known uses, Kevlar is also often used in cryogenics for its very low thermal conductivity, along with its high strength. Kevlar maintains its high strength when cooled to the temperature of liquid nitrogen, 196 degrees C. The table here summarizes the structures discussed in this chapter. This table provides compound names, structures with functional groups in red, and examples that include formulas, structural formulas, ball and stick models, and names. Compound names include alkene, alkyne, alcohol, ether, aldehyde, ketone, carboxylic acid, ester, amine, and amide. Alkenes have a double bond. A formula is C⁻²H⁻⁴, which is named ethene. The ball and stick model shows 2 black balls forming a double bond, and each is bonded to 2 white balls. Alkynes have a triple bond. A formula is C⁻²H⁻², which is named ethyne. The ball and stick model shows 2 black balls with a triple bond between them, each bonded to 1 white ball. Alcohols have an OH group. The O has 2 pairs of electron dots. A formula is CH⁻3CH⁻2OH, which is named ethanol. The ball and stick model shows 2 black balls and 1 red ball bonded to each other with a single bond. There are 4 white balls visible. Ethers have an O atom in the structure between 2 R groups. The O atom has 2 sets of electron dots. A formula is C⁻²H⁻⁵2O, which is named ethanol. The ball and stick model shows 2 black balls bonded to a red ball, which is bonded to 2 more black balls. All bonds are single. There are 5 white balls visible. Aldehydes have a C atom to which a double bonded O and an H and an R are included in the structure. The O atom has 2 sets of electron dots. A formula is CH subscript 3CHO, which is named ethanol. The ball and stick model shows two black bonds bonded to two red balls. The ball and stick model shows two black balls bonded with a single bond, and the second black ball forms a double bond with a red ball. There are three white balls visible. Ketones show a C atom to which a double bonded O is attached. The left side of the C atom is bonded to R, and the right side is bonded to R'. The O atom has two sets of electron dots. The formula is CH subscript 3COCH subscript 2CH subscript 3 and is named methyl ethyl ketone. The ball and stick models shows four black balls all forming single bonds with each other. The second black ball forms a double bond with a red ball. There are five white balls visible. Carboxylic acids have a C to which a double bonded O and an OH are included in the structure. Each O atom has two sets of electron dots. A formula is CH subscript 3COOH, which is named ethanoic or acetic acid. The ball and stick model shows two black balls and one red ball forming single bonds with each other. The second black ball also forms a double bond with another red ball. Three white balls are visible. Esters have a C atom, which forms a double bond with an O atom and single bond with another O atom, which has an attached hydrocarbon group in the structure. Each O atom has two sets of electron dots. A formula is CH subscript 3CO subscript 2CH subscript 2CH subscript 3, which is named ethyl acetate. The ball and stick model shows two black balls, a red ball, and two more black balls forming single bonds with each other. The second black ball forms a double bond with another red ball. There are five white balls visible. Amines have an N atom in the structure to which three hydrocarbon groups, two hydrocarbon groups and one H atom, or one hydrocarbon group and two H atoms may be bonded. Each N has a single set of electron dots. A formula is C subscript 2 H subscript 5 NH subscript 2, which is named ethylamine. The ball and stick model shows two black balls and one blue ball forming single bonds with each other. There are five white balls visible. Amides have a C to which a double bonded O and single N incorporated in a structure between two hydrocarbon groups. One hydrocarbon group is bonded to the C, the other to the N. Amides can also have a H atom bonded to the N, the O atom as two sets of electron dots, and the N atom has one set. A formula is CH subscript 3CONH subscript 2, which is named ethanamide or acetamide. The ball and stick model shows two black balls and one blue ball forming single bonds with each other. The second black ball forms a double bond with one red ball. There are four white balls visible.